And good morning and good evening and good afternoon, everyone, and welcome to our IPCP webinar today on POPs in plastics. It's a great pleasure to see you all here and participate in the webinar today. My name is Martin Scheringer. I'm the chair of the IPCP, the International Panel on Chemical Pollution. And I will give just a brief introduction today together with Roland Weber before we actually get into the content of the webinar. The webinar today is part of an IPCP project on POPs in plastics and their sampling and monitoring. Roland Weber leads this project, and the project is part of or is carried out within a larger GEF-funded project on continuing regional support of the POPs global monitoring plan under the Stockholm Convention. The IPCP supports Roland with the administration and implementation of the project, and we thank Roland very much for all his work to carry out this project as project leader. The webinar today is part 2 of a series of 3 parts. Many of you may have attended part 1 a month ago or so, and part 3 will take place next week on Monday and Tuesday. Today, in part 2, Roland, you may move on to the next slide. Thank you. Yeah. Today, in part 2, the topic is the sampling of plastics from major sectors to monitor POPs in plastics. And then part 3 will take place next week on Monday and Tuesday, and it will deal with the extraction, cleanup, and analysis of POPs in plastics. Part 1 was recorded, exactly, thank you, Roland, very good. Part 1 was recorded, and you find the recordings on the IPCP website here, that you can also go back to that first part where we provided an overview of POPs in plastics. Just as a last bit, the webinars are one of 3 elements of that larger project that we are carrying out with UNEP. The other 2 activities are to prepare a report on the state of knowledge of chemicals in plastics and also identify gaps, knowledge gaps regarding sampling and analysis of POPs in plastics. And then the third activity in the project is actual measurements. So we will collect samples, or we are collecting samples from several UN regions, and then the actual levels of POPs in these plastic samples will be determined as a third element of the project. And I think with this, I can hand over to Roland. I wish you all a productive and interesting webinar today. And Roland will now continue with the actual work plan and timetable. Thank you.
Good day to everybody. Yes, thank you for joining our webinar. Shortly give an overview of the day. First, I will give a presentation on the draft guidance on sampling and screening of POPs in products and recycling, then more detail on sampling of POPs in plastic and major POPs use sectors. Then we will have 3 presentations on the actual sampling of the pellets. First from South America, from Yago Guida, then from Nigeria, from Professor Nnorom, then on sampling in Thailand from Dr. Nudjarin Ramungul. And finally, we will have 2 presentations, one on screening of brominated and chlorinated additives in these plastic pellets. This means already part of the analysis. This will be presented from Dr. Natsuko Kajiwara from the National Institute of Environmental Studies in Japan. And finally, I will do a presentation on monitoring of PFAS in products and recycling, including screening methods of fluorine. So the first presentation is on introduction to the Stockholm Convention, draft guidance on sampling, screening and analysis of POPs in products and recycling. In the first 12 POPs were mainly pesticides and unintentional POPs and PCBs. And only then in 2009, when new POPs were listed, mainly plastic additives, brominated POPs, the PBDEs, hexabromobiphenyl, in 2013, the hexabromocyclododecan, and PFOS, PFOA, and PFAS, which are also plastic related chemicals. have been listed. Early May, additionally, UV328 and Dechlorane Plus have been listed as POPs. So therefore, the control and management of plastic in sectors containing POPs, mainly electronic sector, vehicles and buildings and textiles, become a major task in implementing the convention. This requires screening, monitoring, and separation strategies for POPs containing products and recycling flows. So when we look to the Stockholm Convention, a range of guidance documents have been developed for implementation of the convention. And because of the relevance of monitoring of POPs in the products, also over the last 12 years, one guidance on monitoring of POPs in products and recycling have been developed, and I have been the main author for that. So background of these guidance documents: when in 2009, several POPs used as plastic additives or otherwise in consumer products were listed. And at that time, it was in particular the commercial penta-BDE and commercial octa-BDE. So the Secretariat of the Basel, Rotterdam and Stockholm Convention saw that some monitoring in plastic of electronics and electronic waste in developing countries is needed to better understand the extent of contamination of plastics in end of life and the risk for recycling. And also a guidance document should be developed that support parties in the monitoring, and here especially of PBDEs in products, because the PBDE has been exempted from recycling. So therefore, the BRS Secretariat initiated in 2010 a monitoring activity for PBDEs in cathode ray tubes casings in Nigeria, financed by a small grant project of the Norwegian government. And Professor Osibanjo from the Basel Convention Regional Center in Nigeria and I were tasked to guide and conduct and support this monitoring study. Additionally, I was tasked to develop a guidance document on the monitoring of PBDEs in e-waste plastic. So after I have developed that small PBDE monitoring guidance, the BRS Secretariat was basically satisfied with the outcome and asked if it would be possible to also add 2 more chapters, especially a chapter on PFAS and precursor chemicals, which had also a range of exempted in polymers, for example, carpets, textiles, and time, and also to add a chapter on pentachlorobenzene, where in the POP reviewing committee, a document on the relevance of pentachlorobenzene in some products has been documented. Furthermore, at that time, the government of Japan had submitted documents on the presence of hexachlorobenzene in pigments, for example, here in solvent red. Wait a moment. And this solvent red is, for example, used here in the brake lights and the tail lights of cars. Partly other pigment precursors with high concentration of hexachlorobenzene. So this was the start of the guidance, and these were for the first guidance in 2013, chapter on PBDEs, on PFAS, and on these unintentional POPs. So the guidance was then updated in 2016 and 17, including POPs listed in 2013 and 15. These were hexabromocyclododecan, which has a main use in plastics, in extruded and expanded polystyrene, and also high-impact polystyrene and synthetic textiles. Also, PCNs have been listed, and PCNs have been used as additives, for example, in cables and rubber. So, and also pentachlorophenol, basically, if you want, is mainly used for polymers, but not here the synthetic polymers, but natural polymers like wood and natural polymers like leather. Therefore, for these new listed POPs, major use sectors were plastics and other polymers, including consumer products. And then finally, a third update of the guidance included the POPs listed in 2019 and 2017, which included decabromodiphenyl ether, short-chain chlorinated paraffins, and PFOA. Also here, the main use of PBDE is plastic in a wide range of plastics, and also the short-chain chlorinated paraffins have their major use in PVC, rubber, and polyurethane spray foam. So you can listen to our presentations in the last webinar where we have explained detail on this use. In this updated Stockholm Convention guidance, the circular economy and recycling aspect was included in the guidance and also in the title, because there is a need to circular economy, and globally also there is a push for circular economy, and therefore the recycling of plastic and polymers and the fate of hazardous chemicals and materials become more and more important. So therefore, the document provides guidance on monitoring, including sampling, screening, and analysis of POP content in articles and products in use and in recycling streams for industrial POPs listed 2009 to 2022. There's also some part on the fluorohexanoic acid. And guidance is provided first on articles and products possibly containing POPs listed. Then also it gives guidance to develop strategies for monitoring POPs in products and recycling streams. And also it gives different inventory development aspects, such as determining emission and impact factors. The guidance focuses on industrial POPs, but also it has one chapter, a complete chapter on unintentional POPs. So overall, one chapter about the fluorinated POPs listed, one chapter about the brominated POPs listed, then a chapter on polychlorinated naphthalines, including also PCBs, because also PCBs have been used in products, including polymers. One chapter about short-chain chlorinated paraffins, on pentachlorophenol, salts and esters, and one chapter about unintentional POPs and how to monitor products. So chapter 2 of the guidance gives an overview on general considerations and cross-cutting issues, including capacity building for monitoring POPs in products, quality assurance and quality control, international standards for analysis of POPs. But here, this is a general part, while in the individual chapters, there are then international standards, if available, for monitoring POPs in products. And then here, one section about certified reference standards and materials for monitoring POPs in products. The guidance has a step-by-step approach for the monitoring. So always here, step 1 for the survey of products and recycling streams containing POPs. Then step 2, description about sample collection for the individual POPs. Then step 3, we have described screening technologies in the field or in laboratory. And in today's webinar, we will have 2 presentations on that. And finally, on quantification and documentation of such monitoring approaches. First, on step 1, survey of products and recycling flows possibly containing POPs. So before collecting samples, survey need to be conducted for the monitoring. And here the guidance give an overview on for the individual POPs in what kind of products and material flows they are contained. For example, here in Annex 1, we have an overview of products and major recycling streams. An example here, Annex 1b for PBDEs. So here you have a list, what are the major products which can be screened: electronics, electronic waste, furniture, textile, rubber, and so on. And for each of these uses, also a short description is given here in Annex 1 for all the individual POPs. Then step 2 on sample collection. Here we explain what kind of stakeholders are normally relevant. The stakeholders for such samplings are then listed in the different inventory guidances. And here the guidance on monitoring give a guidance where to find these kind of stakeholder lists in the inventory guidances. Then also how to involve, for example, the customs and research institutions in such monitorings. References is also made to documents which have details on sampling methodologies where available. For example, here one good methodology for sampling of electronic waste plastic developed by EMPA is shortly described, but also then the reference given to find more detail. So the screening for POPs in the field and in laboratory is quite important for the overall analysis of POPs in products, because only a minor share of target products contain POPs. For example, less than 20% of cathode ray tube casings contain PBDEs, or also only a very minor share of carpets or textiles contain PFAS or PFOA. So therefore, products and articles can be screened for the presence and for bromine and fluorine to do a pre-selection, and by this to minimize the efforts of extraction, cleanup, and analysis of samples. Such screening enables relatively cheap and simple pre-selection of article and product groups, and also screening helps to minimize the time and finally the expenses for the confirmation analysis. The Stockholm Convention guidelines for monitoring POPs in products and recycling gives an introduction to the different screening approaches in sampling steps, and it compiles information on different screening methods for bromine, chlorine, and fluorine in products and recycling. When screening methods are applied, it has to be ensured that here the detection limit of the individual screening method is more sensitive than the limit required for sampling. For example, the requirement of a regulatory limit. So here, for example, low POP limit is 50 milligram per kilogram. Then the screening method also need to have a lower detection limit. Otherwise, it cannot be used for screening. Here, for the PBDE, I give you the example what is included here in guidance. So a range of screening technologies have been listed and are described in chapter 4.4, including X-ray fluorescence, where we will see later a presentation also, sliding spark spectroscopy, neutron activation analysis, and others. Yeah, and similar will come later. We have it also for fluorine and for fluorine screening. Especially X-ray fluorescence technology can be used for the detection of bromine in polymers and other materials with a low detection limit, normally below 50 ppm. XRF analysis is limited to the detection of bromine or other elements in the materials, without any capacity to identify, for example, what kind of brominated flame retardant is in. So for that, we need then the confirmation analysis. So it is relatively quick. So within less than a minute, it can be decided if it's useful to analyze electronic equipment or not. And also the relative standard deviation is relatively small, yeah, so that you can decide if it meets a regulatory limit and or not. Then another screening in the field or laboratory for sample selection is the sliding spark spectroscopy. Here, the sliding spark spectroscopy is a surface screening method which by thermal vaporization, ionization, and excitation of surface substrate using a train of high current sliding sparks. Here, give then the atomic spectrum, and this is then detected. And from there, for example, bromine and even fluorine can be detected down to a concentration of about 0.1%. Yeah, this means, for example, that if a regulatory limit here is below 0.1%, then the sliding spark spectroscopy cannot be used as a screening method. Another feature of the guidance is to compile best practice case studies of monitoring of POPs in articles. So where feasible, best practice case studies for monitoring of key product categories, possibly containing POPs, are referenced in the respective chapters and are described in Annex 2 of the guidance. So where possible, case studies or publications were selected with reports available in the public domain, and the link is also provided in these guidance documents. So by inclusion of these case studies, the guidance endeavor to provide information on already performed studies, yeah, and that countries or institutes can build on these. Those case studies can be assessed with the view of selecting the most appropriate approaches and do then a better study. Some case studies reveal that many former applications, for example, of PFAS and PBDE, are not relevant anymore. For example, in current products, but have to be screened in products from the past, and in particular in recycling. So here, an overview on Annex 2. So here we have for all the POPs case studies shortly described. And when then looking into more details, yeah, for example, here Annex 2b, we have about 10 or 20 case studies for monitoring PBDEs in different products, articles, and also in recycling. So in this presentation, I gave an overview on here the first 3 steps. So that was part 1, insight into the guidance. And on the last day of our webinar, I also will give a short insight about step 4, quantification, and what is included here in the guidance document in respect to instrumental analysis of POPs. Okay. So I have to stop this one and then start my second presentation. The guidance can be downloaded from the Stockholm Convention. It is a little bit difficult to find, but we will provide a link at least to the website and some further guidance that you can find the guidance documents, or we can also maybe put a link on the IPCP website. Okay, coming to the second presentation. This is on sampling of POPs in plastic and major POPs use sectors, and some best practice case studies. So first, one slide about sampling of plastic in the environment and in biota, which is not the topic here of our webinar, but which was partly addressed in our first webinar. Then on monitoring POPs in plastic along the life cycle, sampling of plastics in the major use sectors, first electrical and electronic equipment and waste, then the transport sector, the building and construction sector, then some other priority sectors for monitoring, and last to more chemicals of concern ahead for monitoring chemicals in plastic. Like I said, one slide. This presentation addresses sampling of plastic in use sectors and related end of life of major sectors of POP use in plastics. So therefore, it does not address sampling of plastic in the environment. Major sampling in marine environment is described here in the UN document of Gesamt, yeah, where I also give here the link, and we can give it in the chat. Also, the global plastic pellet sampling of Professor Takada was presented in the first IPCP webinar, in which series and can be found in the recordings and on his pellet watch activities and publications. And also this presentation do not address sampling of plastics in biota, including humans. The sampling of plastics in marine related biota was addressed by Professor Takada in the first IPCP webinar in this series, including monitoring of POPs in individual plastic pieces and related contamination of biota. And I would recommend to look here to his presentation and also then to his publications. So when we look for sampling of POPs in products and look to the individual POPs, one approach is doing market surveys of the POPs used, and especially those POPs which are still in production and use. So for those, market surveys can be conducted. One best practice market survey here for short-chain chlorinated paraffins have been conducted by Beijing University, where they have screened 124 products, including the major use sectors, PVC, rubber, polyurethane spray, but also paints, leather, metalworking fluids, and then to see what is the detection frequency, what are the levels, and so on. So that's one approach. In this presentation, I will suggest as a major approach another one. This is to look for POPs in products in the life cycle, and therefore look and screen different POPs use sectors. For all POPs listed, also for those where the production already have stopped, the monitoring in the life cycle of products in use can still be relevant. And for all the POPs, the monitoring of waste and of recycling is relevant. For those POPs which are still produced, this includes PBDEs, short-chain chlorinated paraffins, PFOA, UV328, and Dechlorane Plus, and used as plastic additives or are associated to plastics. Also, current market surveys can be conducted. So here, when we look to the major sectors and to the life cycle, the major sectors are for POPs in plastic use are the building and construction sector, the textile sector, the transport sector, and electronic and the electrical and the electronic sectors. So these have by far the major POP use as plastic additives. So first, some monitoring case studies and monitoring of POPs in plastic in electrical and electronic equipment, which is a major use or was a major use of the brominated flame retardants, but also Dechlorane Plus and UV328. So the sector is huge. In 2019, we had more than 53 million tons of e-waste plastic, including about 10 million tons of e-waste plastic. And in 2030, it is assumed that about 74 million tons of e-waste will be generated, which will contain around 15 million tons of e-waste plastic. But only a fraction of this e-waste contain POPs. And these e-waste and e-waste plastic are mixed with other equipments and therefore contaminate overall the entire plastic. So therefore, detailed information on contamination of different categories by monitoring data are needed. And then this kind of information need to be documented and finally reach the people which are managing and recycling e-waste plastic. So major POPs in e-waste plastic are the flame retardants, the PBDEs, Dechlorane Plus, still produced. Then polybrominated biphenyls are not produced anymore and used in small amounts, therefore not relevant. Then we have the short chain and chlorinated paraffins, and also the POP candidate medium chain chlorinated paraffins, which are used in cables, PVC parts and rubber parts. We have PCBs in cables, but in electronics also in condensers. Also polychlorinated naphthalines have been used in cables, but only for electronics produced before the 1980s. And we have the UV 328 UV stabilizer in plastic in electronics. Also, there are a range of other pollutants, and some of these pollutants are also relevant for other conventions like Minamata Convention for mercury, or the Montreal Protocol, or climate change conventions. So therefore, when doing a screening in electronics, one part can be focusing on plastic and POPs, but overall it is useful to consider the larger area and possibly include also other pollutants in that screening. For screening of a best practice screening of products in consumer market, here for electronics, I would like to highlight the Swiss study, where the Swiss authority monitored 2,000 consumer products for the presence of brominated flame retardants as a major product categories, but also they screened building materials and lighting equipment. And the aim of the survey was to evaluate the compliance of commercial products with a provision to the Swiss restriction of brominated flame retardants. And when you look here to their approach, yes, they also used first a screening approach for bromine in products to indicate if the product contain brominated flame retardants or not. This screening has been done in laboratory. Then as a second step, they used the GCMS analysis. And here they screened those commonly used flame retardants. And in a third step, they used non-target screening for bromine positive samples where the brominated flame retardant had not been detected by this target screening of the known flame retardants. So the study showed that the PBDE content in current products in Switzerland, that was around 2010, was small. In total, from the 2,000 products, only 17 samples contained DKBDE above the restriction threshold of 0.1%, and only 2 of the products, this means about a per mil, contain commercial octa-BDE above the threshold of 0.1%. Another best practice case study, but here now in the life cycle at the end of life, is a screening of cathode ray tubes, TVs, and also computers. in Nigeria. So that was just finally the outcome of the project I mentioned in the beginning. So here the students sampled more than 380 cathode ray tube casings, and then they compiled information about manufacturer, brand model, serial number, year and origin of production. And the aim was here to understand first the formal use of the PBDEs, octa-BDE and deca-BDE, as well as other BFRs, but also to understand if there's a different distribution in different region of production. So the approach in this study was also a pre-screening first with the XRF for bromine, and then confirmation analysis with GC-ECD, and also with GC mass spectrometry. So I think that was a very nice case study for South-North cooperation between Nigeria, Germany, and Sweden, and we will have more details about this tomorrow. So the size of this case study were nearly 400 individual CRTs. And when we look back, this was really the minimum number to roughly get a statistical insight into the distribution of deca-BDE. So we found in total about 30% of the CRTs were treated by deca-BDE, and especially of the less used commercial octa-BDE, where we, from the around 400 individual CRTs, only 5 has been treated. So you see what kind of effort for individual electronic is needed to get a kind of statistical relevance. Yeah, so probably better would have been 1,000 individual CRTs, but also already you can imagine to screen 400 and analyze more than 200 different CRTs is quite a work. So therefore, unfortunately, there are not many of such case studies. Then another best practice case study here from the UK. So when you look to electronics, most electronics consist of several plastic parts. Yeah, so our CRTs, they had one major plastic part, so there the screening is simple, but often only a few of these parts of most electronics are composed of several plastic parts, and often only a few of these parts are flame retarded. Therefore, some screening of plastic parts might be needed of the individual plastic parts. So here for the CRT casings, we have, let's say, 2 major parts. One is here the CRT casing, and here the stand. And what have been found that the stand of the CRTs are normally flame retardant free, and here the big part, big plastic part of the CRT casing, this is frequently flame retarded. When we go to other equipment, they can contain 5, 10, 20 different plastic parts. And there are actually nearly no case studies which really look into the nitty-gritty of such complex electronic and electronic equipment. So therefore, I would like to introduce here to a best practice study to monitor here the PBDEs in large and small electrical and electronic equipment for UK and for Wales. So here they did a screening, for example, of plastic parts of fridges, which showed that only a very few pieces in some fridges contain high levels of PBDEs. And these were the plastic parts of electrical and compressing casing, of the electrical junction box, and of the cable box. But that the major outer plastic parts, this mean the door, side panels, back trays, and shelves, and so on, does not contain brominated flame retardants. Yeah. So this kind of information is important from different perspectives. I mean, one, yes, to understand the subject of flame retardants and of possibilities of separation, but also about recycling or depollution of such an equipment. Yeah. Also, they did this for other household appliances, like for washing machines and dishwashers. And also here from washing machines and dishwashers, only a few controller boxes contained brominated flame retardants, while all other major plastic parts did not contain brominated flame retardants. So from this kind of studies, I think more monitoring studies are needed. And here they only monitored for the PBDEs, but this kind of screenings are also needed, for example, for the new listed POPs UV328 and Dechlorane Plus, yeah, that we understand how we can depollute such electronics when it goes into the recycling. Another kind of screening for electronics is shredding. So the major amount of plastics in the major electronic categories, large household appliances like freezers, refrigerators, air conditioners, washing machines, small household appliances, including microwaves, oven, toasters, then ICT equipment, computer screens, copy, fax machines, scanners, and also then in consumer equipment, TV, CRTs. So these are the major plastic uses of electronics. And to understand here the content of PBDEs, one good approach is to screen the shredded fractions from individual electronic categories. So from this kind of screening, then also impact factors can be derived, for example, for the inventory development. So in electronic waste recycling, normally the e-waste is frequently shredded and the metal fraction separated with a remaining plastic fraction with the impurities. But also, if electronic waste is manually dismantled, this means the plastic is manually dismantled, finally the plastic needs to be shredded for economic shipment and further processing. Therefore, this kind of plastic shreds from electronics are a major target for the monitoring. And major samples from electronic plastic is to be gathered and analyzed often from such shredded plastic, which gives overall an average overall contamination level, or so-called impact factors. To understand of POPs, PBDEs or Dechlorane Plus contamination in such plastic fractions, decide if a plastic shred can be used in recycling or needs further separation, considering, for example, Basel Convention low POP limits or national regulations. So one complexity here is the correct sampling of e-waste plastic shreds. And this needs to take in account different interrelated issues. First, the distribution of contamination of POPs in waste products and in waste fractions. Then the statistical question of the determination of the size of a representative sample and the chemical characterization of particles and samples. So to develop such a monitoring of shredding fraction is highly complex. And overall, I see only one best practice case study, and this has been done more than 12 years ago by the Swiss Material Testing Institute, EMPA, which developed here a standardized methodology for sampling of electronic plastic for the survey of POP BFRs and other regulatory substances in the RoHS regulation. So here, to be at a statistical level, they concluded that for one sample, 3 to 7 tons of plastic shreds which need to be sampled. And best from a monofraction. This means we want to understand what is the PBDE level, for example, in TV casings or in flat computer monitors, yeah, or the average concentration in fridges. So for all these kind of shreds, 3 to 7 tons of mono shreds have to be produced. And then the description from them is that 20 single samples then are taken from these 3 to 7 tons, and 10 samples are then mixed together in a so-called heap method. And finally, this heap method is flattened and watered, and finally only a small part is brought to the laboratory. And the amount of samples which need to be taken here depends on the particle size. And here the Swiss guidance, but also the Senelec standard give a description how many liters finally for which size of particles need to be sampled, that the sampling is halfway or is statistically correct. So you see here the complexity of these kind of samplings and screenings, and you understand also why, unfortunately, so few studies are available. Yeah, but here I would encourage you that more studies are conducted, and at the moment we only have mainly emission factors here from the Swiss study, here for the PBDEs, for the different main categories, cooling, freezing appliances, where, for example, no octa BDE has been found, but DK-BDE below the regulatory limit, and only for CRT monitors and for CRT TVs, the average concentration of here DK-BDE were above regulatory limits, while in the whole screening of electronics, no commercial penta-BDE has been detected. Why? Because penta-BDE is not used in normal plastic, but rather in polyurethane foam. So from this study then, I have used the impact factors for the inventory guidance. And additionally, there was another study from France, which had developed some impact factors for flat screen televisions. But really, when I developed here the inventory guidance for the PBDEs, these were the only studies which really gave statistically relevant impact factors which could be used. Another interesting samples for screening PBDE in plastic are recyclates. Relevant plastic samples for analysis are here recyclates or plastic pellets from recycling, which are imported and which are used for the manufacturing of new plastic products in a country. So here there is also a lack of screening. We have only one study published on monitoring here of PBDEs and UV 328 from IPEN from 2021. And this was also one reason that UNEP in our project decided that we do mainly focusing on monitoring POPs in such plastic recyclates. So here, plastic recyclates can also be pre-screened with the XRF. We will hear later on from Dr. Kajiwara, and then those which are positive for brominated, for bromine can be analyzed for the brominated flame retardants. Those which are positive for chlorine can be analyzed for Dechlorane Plus. And for UV 328, at the moment, we do not have a real screening method, so all of them would be then analyzed for UV 328. And a last screening and relevant product are consumer products, which are finally produced from such recycled pellets. So plastic containing PBDEs is recycled often into products, including sensitive consumer products, such as toys, food contact materials, and other goods, documenting a wide range of research studies. So here, when you see which of the consumer products have been found positive in such screening studies, you see it's often a black plastic. So this is because recycled plastic is often relatively dirty. So therefore, by addition of carbon black, you get a homogeneous materials, and therefore often these black plastics are contaminated. You see, you have here some highlights, hangers screened by the study from the National Institute of Environmental Studies in Japan, up to 10,000 milligram per kilogram. This gun for kids, 2,800 milligrams per kilograms of PBDEs, or from a study from IPEN, toys in Africa, contained 270 milligram of PBDEs, but also nearly 7,000 picogram TEQ of brominated dioxins. One example here from the study of Kajiwara et al. Here a negligee for children, where also you see that colorful other plastic can be contaminated from recycling with PBDEs. So a best practice study I would recommend you is here from the National Institute of Environmental Study from Japan, which have monitored more than 1,100 consumer products from 18 countries, and which have been presented in our first IPCP webinar and have been recorded, and you can find it on the IPCP website. So further studies are needed, especially now, including the new POPs, UV328 or Dechlorane Plus, because most of the studies here for POPs focused on the PBDEs. Coming to the second major use, the transport sector and monitoring in the transport sector. In addition, the transport sector contain a part of POP-treated textiles in the seats. So here, when you look to the overall plastic amount in the 1.3 billion vehicles which are currently on the road, we can estimate with 200 kilogram of plastic per vehicle that we have about 13 million ton of plastics and other plastic waste in end of life per year. And in total, we have about 65 million end of life vehicles per year. Also, a range of POPs are present in plastics and synthetic textiles in the transport sector, including again the flame retardants, chlorinated paraffins, also PCBs in cables, but also in condensers, and UV328, a major application, have been in vehicles. There are again other pollutants in this category which can be considered in such monitoring studies. Unfortunately, there is no monitoring studies of POPs in new vehicles. So therefore, I would recommend that more studies on, or that studies of POPs in new vehicles are conducted. And a good starting point for monitoring could be here the exemptions of the uses of POPs listed in the Stockholm Convention. For example, for PBDEs, there are exemptions and therefore uses in powertrains, in fuel system applications, in the pyrotechnical devices, in terminal fuse blocks, in cable jackets, but also electronic equipment in vehicles, and fabrics and textiles. Also, for monitoring new vehicles, we can look to the exemptions of Dechlorane Plus. So Dechlorane Plus is contained here in wire harnesses, mass wires, tapes, in many parts of underhood and powertrains, applications in vehicles. Yeah, so we know this and we know the exemptions, but we do not really know the share of parts which are treated. Yeah, so here studies are needed. Also, Dechlorane Plus has a specific list of exemptions which can be screened through. And in addition to the motor vehicles, Dechlorane Plus got exemptions for aerospace, space, and defense. Yeah, so also those areas could be monitored, although they are, of course, not as relevant as the normal vehicles due to the smaller amount of such materials. When we look to the UV 328, also it has been listed with a range of exemptions. And so also here, exemptions can be screened. So here, the main use of UV 328 is in outer parts, including bumpers, grills, sunroofs, spoilers or wheel caps. Inside cars, for example, these are the displays, but also here we do not know what share of these parts are used, because overall there are more than 20 different UV stabilizers from the benzoazoles. Yeah, so here monitoring studies are needed. There are monitoring studies for end-of-life vehicles, but here mainly for the old POPs. So here, when doing monitoring of individual vehicles in the end of life, it is useful to get information about the age distribution of the use of POPs in vehicles, the regional distribution, and also it would be interesting to find out if there is an association of certain companies of the use of POPs. So therefore, when doing studies on end-of-life vehicles or vehicles in use, it is useful to understand or for the results to also include the year of production of such vehicles and parts in vehicles, the producers and the model names, and the country of origin. The country of origin, because several producers are producing in different regions in the world, but for example, there are flame retardant standards for some region in the world, so therefore the use of, for example, flame retardants can be quite different in different regions. So this information would be useful if doing a study of screening of POPs in vehicles. Also here, unfortunately, we have only one best practice case study for monitoring POPs, here PBDEs and HBCD in end-of-life vehicles. So this has been conducted by Dr. Natsuko Kajiwara from National Institute of Environmental Studies. So they screened PBDEs and hexabromocyclododecan in 115 parts in 45 vehicles produced between 1993 and 2012. In the first step with the XRF approach and then analyzed in the laboratory. So this included dashboards, floor mats, floor covering, plastic parts in seats, door trims, headliners, car fabrics, and polyurethane foam. So the result was in the XRF screening that 32 out of the 515 materials investigated contain more than 0.1% bromine, and 16 of these products contain hexabromocyclododecan or polybrominated diphenyl ethers above 1%. So the major component which were treated here for PBDEs were the seat fabrics by far, then a bit in the floor covering and soundproof materials. But the soundproof materials, the levels were less than 10,000. This means the soundproof materials were produced from recycled products. For commercial penta-BDE, there were only 2 samples positive. So these were from from US cars, and especially in the polyurethane in the seat, and here also a bit in the seat fabric. For hexabromocyclododecane, from all the 500 parts, only 2 were detected positive, and they were floor coverings. And therefore, it was revealed that here the HBCD use were relatively minor. Interesting is also to look in this study to the overall bromine screening. So here, these are those which contain 1 to 5% and 0.1 to 1%, which were only 2% and 4% of the total parts screened. But then there were 60 out of 500 parts, this means more than 10%, had bromine content between 0.01% to 0.1%. And 260 out of 515 parts had a bromine level of 5 to 100 milligram per kilogram. This indicates that more than 50% of interior plastic had a secondary brominated flame retardant contamination. Yeah, it is not clear if this was all because of recycling or if we also get evaporation from some parts and contamination of other parts. Yeah, so here also more to be done in the screening of vehicles. So similar screening of cars from other regions are missing and are needed. And for such screening, then also other POPs and chemicals of concern could or should be included. Then, like for the electronics, another possibility for screening POPs in vehicles is the screening and sampling of light shredder fractions for end-of-life vehicles. In industrial countries, the shredding of vehicles is the main treatment for end-of-life vehicles. So after shredding, the shred is separated in a heavy and a light shredder fraction. And the light shredder fraction, which is about 15 to 25% of the shredder, contains plastics, polymers, textiles, and rubber, including also some glass and so on, and including the POPs. So this light shredder fraction can be sampled and analyzed then for PBD, HBCD, but also fluorinated retardants, Dechlorane Plus, fluorinated paraffins. So unfortunately, other than for electronic plastic shredder, there is no standardized methods developed to generate a representative end-of-life vehicle light shredder sample. So there is a European guidance document on how to perform a shredding campaign, and they suggest to use about 100 vehicles for a campaign, which would then result finally in 20 to 35 tons of shredder light fraction. But it is quite challenging to get then here a statistical fraction out of it. Yeah, so here I think more research and also more standard setting work is needed. One problem here with the car shredder is that the size fraction of car shredder is relatively large, and this makes it much more complicated to get, let's say, a homogeneous shredder fraction finally for analysis and for determining POP amount, for example. But there are studies which are at least measuring it. And here, this is also from the inventory guidance from the Stockholm Convention, which I have included here. The most studies come here from Japan. And the Japanese have then shredded cars produced before 1996. In another campaign, cars produced before 1999. And in a third campaign, cars produced after 2000. And the levels are halfway consistent. Yeah, so you see that here, at least, I think the Japanese have a methodology to get a halfway reasonable shredder fraction out. And what we also see is that the DKBDE on the PBDE levels are decreasing here over time. We have also shredder fraction studies from Europe. Here one from Netherlands, which put here 10 milligram per kilogram of DKBDE, but give then a range of 0.1 to 70 milligram per kilogram. Yeah, and here you see what kind of variation they found in their study. Coming to the last large industrial sector of POP use in plastic and other polymers, which is building and construction. When we look to building and construction, we see the major plastics in buildings are PVC and expanded and extruded polystyrene, EPS, XPS, polyurethane, and polyethylene. So for EPS and XPS and polyurethane in buildings, we know that they are frequently flame retarded. For EPS, XPS, mainly HBCD has been used until recently. And for the others, partly polybrominated diphenyl ethers have been used. But they are also here only a fraction of the use of flame retardants. But for example, halogenated phosphorus flame retardants are used in average in higher concentration here in the insulations. When we look to PVC, which contain often a high amount of additives for soft PVC, including fluorines, partly POPs like chlorinated paraffins, but also other restricted endocrine disrupting chemicals like DEHP, phthalates, and DBP are used. So while we know which POPs were used and know their concentration in the treated material, the overall amount of most POPs in building is unclear. Yeah, for HBCD, we have data because 90% of hexabromocyclododecane has been used in insulation foams. But for most other POPs, we do not really know how much of the PBDEs for what kind of material application is there. Yeah, what we know is that if, for example, DKBDE is used in polyethylene insulation foam, the concentration is around 20%. Yeah, but overall, there are not really detailed studies on, for example, flame retardants in building materials. There are some studies of individual POPs in plastic, which I will show a few, but there is no systematic studies covering a range of POPs in building materials. For example, also or in end-of-life plastic materials. So there are some studies which focus on a few particular POPs, for example, screening of PCB in sealants in buildings or hexabromocyclododecane. So therefore, since there was no study, we have now initiated a study of monitoring brominated flame retardants in building materials at the end of life with the Technical University of Vienna. And the approach what we are taking there is also first sampling in a recycling center and screening with XRF, and then in a second step, then the analysis in the laboratory. But at the moment, we are just at the XRF screening. Yeah, I tell you that also to encourage others to do some of these studies because there's really a lack of data. There are some studies of building materials on the market. And one of such studies from the Netherlands on screening of polyurethane foam for chlorinated paraffins, short, medium, and long chain chlorinated paraffins in 1 and 2 component spray polyurethane foams. And what was found here is that many of these foams contain medium chain and long chain chlorinated paraffins up to 50% and 29% respectively. No short chain chlorinated paraffins were used in polyurethane spray foam in the European study. But I showed you in the beginning the general monitoring study in China. So they have found both short chain and medium chain chlorinated paraffins in their monitoring study. And also here, useful to do screening of other hazardous additives. So here for polyurethane foams, the organophosphorus flame retardant TCLPP was detected in 18 out of 24 foams and at a level of up to 30%. Another just current study, and this slide has been presented just this month at the CTEX conference in Ireland from Helene Wiesinger from ETH Zurich. So she is screening also new polymers, here PVC, in floorings in Switzerland, in total 150 samples. So first they screen if the polymer type is the right one, then they screen for phthalates, then they are looking for alternative plasticizers and others for elements, and they are doing biological activity monitoring. So therefore a very comprehensive study for one polymer in buildings, which I also would consider a best practice study. And here in this study also they might look for POPs like short chain or POP candidates like medium chain chlorinated paraffin here in their screening approach. There are only a few studies of screening POPs in use. One best practice case study is from Switzerland. So Switzerland did a national-wide comprehensive screening of PCB in polymer sealings in buildings, Kohler, in 2005. So here they screened more than 1,300 joint sealants from concrete buildings between built between 1950s to 1980s, and nearly 570 samples. This means 42% exceeded the limit of 50 milligram PCB per kilogram. Yeah, so you see how relevant here for Switzerland, but also for Germany, the use of PCB in these joint sealants have been. PCB concentration were above 10,000 milligram in 21% of the samples, and above 100,000 milligram or 10% in also close to 10% of the samples. So the study revealed the use of PCB in joint sealants was common construction practice between 1955 and 1975. Yeah, so you see here, they have also looked to the age of buildings, and they found that, for example, buildings built 1976 to 1980s do not contain PCB. Yeah, so this kind of information should come out of such screening. In a subset of 85 samples, they also investigated if the XRF approach would be appropriate. And so here, the detection limit for PCBs is 10 to 25, or for chlorine is 10 to 25 milligram per kilogram. But then they found that they have many false positive. And most of these false positive were chlorinated paraffins. So at that time in 2005, they said that this XRF screening of sealants are not useful because there are so many false positives because of the chlorinated paraffins. But now chlorinated paraffins are also POPs. So therefore today a XRF screening of sealants for chlorine in buildings, I think is quite useful, and different POPs can be detected from such a study. Then important would be more studies on screening of POPs in end of life of buildings. So here, for example, for Switzerland and Germany, we have regulatory limits even. But when I did my project for Germany, which was related also to buildings, I found that there was basically no real study which were screening PCBs in end of life concrete in buildings. Yeah, so also here a lack of monitoring studies. But what we have here in Germany and in Switzerland is our guidance documents on the assessment and deconstruction of buildings, and the monitoring of buildings and the monitoring of building materials. Yeah, so we have the guidances, and of course, when buildings are demolished, so they are screened, at least in industrial countries, but this is often, let's say, for commercial use and not published. Yeah, so here I would also encourage that more research studies are done and published. So now we have looked to these, let's say, major use sectors, but there are some other priority use sectors where POPs monitoring would be useful. And these are, for example, toys and other children products. Also screening of POPs in furniture would be useful. In America, some of these screenings have been published. And also medical devices now have more frequently POPs, including the fluorinated POPs, Dechlorane Plus, but also, let's say now we have much PVC in medical devices, and I have not really seen a screening study which have looked if chlorinated paraffins can be found there. So these priority sectors, the list here is from our recently published study on chemicals in plastic from UNEP. Here I have also the link. And while we are focusing in this webinar on POPs, the need of overall assessment of chemicals of concern in plastic is much, much bigger. So POPs are only the tip of the iceberg. So in our technical report, we found that there are about 13,000 substances which are associated with plastic, and 3,200 of these 13,000 plastic have a potential concern because they have at least one hazard property. So here, therefore, useful to look to 10 groups of chemicals which have been now identified by these publications: flame retardants, PFAS, bisphenols, alkylphenols, UV stabilizers, biocides, PAHs, phthalates. And when conducting such plastic monitoring study, then to possibly look broader and not only to the POPs. So they need to be considered for the management and also for improve the safety of plastic. Thank you for your attention. Okay. So the next presentation comes from Dr. Yago Guida. He's postdoc at the National Institute of Environmental Studies in Japan and is at the moment monitoring POPs in plastic and is involved and a part of our study of POP in plastic from UNEP, and was responsible to organizing the pellet samplings here for South America. So therefore, over to you, Yago, and to your presentation.
Thank you very much, Roland. Thank you for the nice introduction. So good morning, good afternoon, good evening, everyone that's here watching our presentations. It's a pleasure to be talking to you today. So my presentation will be briefly about the sampling of plastic recyclates in the selected countries from the GRULAC regions, more specifically in 3 countries from South America. And also I will present some information on the recycling situation in Latin America and also in the 3 specific countries. So first, I would like to present the scope of the presentation. I will present an overview of plastic production and recycling in the GRULAC region, also which were the 3 selected countries, something about the production and recycling in each selected country, our sampling experience in the 3 selected countries, and pellet samples collected for the UNEP GMP project. So Latin America encompasses approximately 4% of the global virgin plastic production. It's not much, but the production of virgin plastic in Latin America, it has been increasing following the global increase. The largest global sector for plastic production in Latin America is packaging, and it corresponds to almost 40% of the total production, followed by building and construction and others, which include appliance, furnitures, medical plastics, and so on. And the overall average of plastic consumption in Latin America, it has been estimated at 32 kilograms per person in 2017. And here it's a map of the GRULAC region. For those that do not know, it does not only include South America, but also Central America up to Mexico. So there are several countries in the region. And according to the World Bank, the Latin America and the Caribbean region generates 11% of the world's municipal waste. So the Latin America region has the third highest per person waste generation rate at approximately 1 kilo per person per day. It's only less than North American and Europe and Central Asia. And this general generation rate is also higher than the global average, which is 0.74 kilos per person per day. And based upon data from the World Bank, also 81% of the waste generation in Latin America region is collected, and 84% of the population has waste collection coverage. But the problem doesn't lie on the collection itself, but mostly on the waste management after the collection. So Latin American countries, Latin America as a region manages waste by 27% using open dumping, almost 70% landfilling, which is half of it sanitary landfill, 15% controlled landfill, and a little bit like 1.5% unspecified landfills. So there are several uncontrolled landfills also in Latin America, and only 4.5% of that collected waste is recycled, and less than 1% is used for composting and incineration. So the practice of open dumping in Latin America region range from 4% reported in Colombia to 84% reported in Trinidad and Tobago. So the poorer the country, it's more common that the waste will be open dumped and disposed of in regular conditions. And here in this map, we can see, for example, that some of the countries like Brazil, we are generating a lot of plastic waste, but if we compare the generation rate by kilo per person per day, Brazil is not the highest values here, but the situation is more critical in the Central America region. So the Latin America region was the fourth highest plastic scrap exporting region out of 8, with 5.9% of exports between 1988 and 2016. And the region was the third lowest plastic scrap importing region out of 8, at 0.8 of imports in the same time period. And cumulatively, over the 28 years, the region has exported almost 13 million megatons and imported almost 2 million megatons. So we can see that the Latin American region is not very much into importing plastics, although there is some importing for plastic scraps. But it's also exports it probably for other countries in Africa or Southeast Asia. It's not clear for me yet. So regarding the imports and exports, Mexico is the most relevant country. So it has been responsible for over 8% of the total exports of plastic scraps in the region, and also responsible for almost 6% of the plastic scrap imports in the region, followed by Brazil, which accounts for almost 6%. One problem is that most of the imported plastics are classified as other plastics in the Contrade database, and within those other plastics, PET and PP are reported to compose most of it. But after PET and PP in the category, or after the category of other plastics, PE, PVC, and PS are also the plastic polymers mostly imported into South America, or Latin America. So considering the poor plastic management and the environmental contamination in the region, we have that this region has a lot of shorelines and huge extensions of shorelines. And most of those plastics that are managed in an environmentally sound management way, so they can end up in the environment. And considering the marine litter most of it that has been found in the region has been related to single-use plastics. So here we have the top litter items in the Latin America region for the Ocean Conservancy International Coastal Cleanup in 2018. So we can see here all of them are single-use plastics, and also from another institution comprised from the Marine Debris Tracker database from 2011 to the present. It's the same, most of it, some single-use plastics, some aluminum cans, and also plastic fragments. And here again, we can see a very high rate of mismanaged plastic waste in terms of kilogram per person per day in the Central America region. But the highest rate of mismanaged plastic weight in total, in terms of total metric tons, it's here for Brazil. Argentina is also quite relevant, and Mexico and some other countries. So the selected countries for this project that we try to cover within the GRULAC regions were Brazil, Argentina, and Chile. They are three of the largest and most industrialized countries in South America, and together they hold a total population of over 280 million people, with the largest parts living in urban areas. And these three countries, they were selected based on the sampling viability. It doesn't mean that we didn't try to sample in other countries, but those were the countries where we have some contacts and some people willing to go for the sampling campaigns, which quite time consuming and sometimes a little bit challenging, as I'm going to show you later. And some other countries, they were consulted. So I have colleagues in Colombia, in Ecuador, also in Uruguay, Paraguay, but I couldn't find anyone that was really willing to help with that. But there might be some other countries from the GRULAC region within this project that they were contacted through their focal points for the Stockholm Convention Center, and those samples might be used for PFAS analysis in the Spanish laboratory. So regarding the first country that we selected for sampling in the GRULAC region, the first one was Brazil. It's important to say that Brazil has one of the highest waste collection rates, although a minor part is recovered, which means that most of it is just disposed of in landfills or dumping sites. And plastics, they represent almost 14% of the collected waste in Brazil. It's most of that waste is like organic waste and some other stuffs. And here we can see that for the municipal solid waste, the final disposal sites, most of it is landfill, followed by open dumping and sub-regulated landfill. And from the 79 million tons of urban solid waste generated in the country in 2018, it was estimated that almost 40% had inappropriate final destinations, almost 6% were landfilled, and only 2.2% were recovered in sorting facilities for further recycling or transformation. And the Brazilian government intends to eradicate all open dumping sites in the next 3 years. However, there are over 2,000 open dumping sites operating in the country. So it will be quite a challenge. And Brazil is now considering to start burning waste, which has generated some debates in the country. But it's imperative to better regulate these dumping sites in the country. So only approximately 22% of the Brazilian municipalities have waste selective collection, which attains around 70% of the population. So due to the high rates of poverty in the country, Brazil has an impressive number. Sorry, there's something on my screen. Impressive number of waste speakers. It's over 600,000 waste speakers in the country, who are responsible for most of the waste collected from the streets, irregular dumping sites and landfills, and that are destined to reuse, transformation, and recycling. And here it's interesting to say that although there is a huge workforce for waste collection from those waste pickers in the country, they are generally focused on the kinds of waste that have more commercial value. So for recycling, it would be metals, aluminum, even paper and PET bottles. They would have a higher market value than other plastics that could be more impacted by persistent organic pollutants. And Brazil was the fourth largest producer of plastic waste in the world in 2016, with approximately 2 million tons, surpassed only by US, China, and India. And the World Bank has said that only 1.3% of the waste generation in the country were sent for recycling. And this is one of the lowest rates in the world and well below the global average of 9%. However, there is some opposing information regarding plastic recycling in Brazil, according to the National Association of Plastics, which stated that approximately 24% of all plastics for end consumer use was recycled in Brazil in 2021, corresponding to 1.1 million tons of plastics. And this value, according to the report, was an increase of 15% when compared to the previous year. So it's interesting to see that different sources can present very different numbers, very different figures here. So it's important to consider, maybe in this case, I would stay with the national data. And besides PET and other specific polymers that can be collected in large amounts and have well-known composition, the plastic recycling flow in Brazil is mostly limited to industrial scraps and waste, which means that for other kinds of plastics, besides PET and some industrial scraps and waste that have very high amounts and pure composition, where people know what kind of plastic that is. So most of the other plastic that goes in the municipal solid waste management or end up in landfills, dumping sites, they are not really picked for recycling by those waste pickers. So here there is some logistic flow that shows, for example, that the consumer, it will get some plastic, it can end up being collected by the prefecture, public system. It can be collected by waste pickers if disposed of in some regular place, or by private companies that are starting to collect pre-selected waste in Brazil. And from the waste pickers and the public service, it goes sometimes for some cooperatives of waste pickers where they will sort it, and it's generally transferred for some intermediary facility where they will separate and also process, like crushing, powdering, sometimes even make pellets before going for recycling itself. So most of the contact that we managed to make in Brazil were with those intermediary recyclers, where they receive it, they separate, they clean it, they process it, but they do not really transform it into a new product. And that was also true for Argentina and Chile. So regarding plastics related to POPs in Brazil, it's important to mention that Brazil stands out in South America as an e-waste generator. We have been generating a lot of e-waste in the country. It has been estimated that 2,140 million tons of e-waste was generated in Brazil in 2019, primarily in the southeast region, which is the richest region of the country. And although Brazil announced an e-waste federal regulation in 2010, a formal e-waste reverse logistics system with the structure for collecting and recycling is absent in most regions. And hence a large share of the e-waste generated is still disposed mixed with household waste in landfills and is designated for informal chains of recycling. And besides the imports In 2018, Brazil produced approximately 8 million tons of thermoplastic resins and 7 million tons of transformed plastics. And here we give some attention for PVC, as Roland just showed us, that is quite can be related to short-chain chlorinated paraffins that are listed under the Stockholm Convention. So although PVC recycling has increased at a rate of 11% per year since 2015 in Brazil, only 17% of the PVC generated post-consumption were recycled in 2014. Thus, from the 134,000 of post-consumption PVC generated in that year, nearly 23,000 tons were recycled, and the rest of it was probably disposed of in landfills, mostly. In Brazil, 70% of the industrial rubber is used in tires, and in 2016, manufacturers and imported destined around 5,000 tons of tire rubber. Around 70% of unserviceable tires collected in the country are removed from the environment and transformed into alternative fuel for 24 cement production units. So it's basically used as fuel for those cement production. But also some minor part of it goes for as granulated rubber for courts, sport courts, and also playground rubber tiles and this kind of thing. So energy recycling is completed by the use of rubber in flooring, carpets, and rubber asphalt, which together absorbs the other 30% of the volume collected in some specific points for tires collection in the country. And regarding the construction and demolition waste, which can be imported for SCCPs, PVC, PCB, PCN, as Roland just mentioned. So municipal cleaning service collects about 122 tons of this kind of residue per day in Brazil, but only 8% of all construction and demolition waste collected was designated for recycling. However, the real production of this kind of waste is unknown in Brazil, and most of it is probably used for embankment. And one positive news regarding plastics related to POPs that are well managed in Brazil, we have that 94% of agrochemical packages, they are properly managed in the country because there is a law that has regulated a few years ago how to properly manage agrochemical packages. So the second country was Argentina. And there is no complete official statistical data on plastic recycling in Argentina available on the web. And the plastic recycling industry was born in the 90s and has been growing the last 15 years. However, most recycling industries are concentrated in the metropolitan area of Buenos Aires, which is the capital and holds most of the Argentinian population. Mechanical recycling is the most popular there. And the identification of plastic types and plastic produced in Argentina is voluntary. So there is no legislation that requires their use, which makes household separation and recycling quite difficult. So Argentina is one of the countries with the highest plastic consumption per capita in Latin America, but after Brazil. And of the almost 2 million tons of plastic consumed, only 13% were recycled. So the recycling rate is similar to Brazil. We have that for PE, 24% was recycled. For PET, 21% was recycled. It was surprising for me to see that PE was more recycled in Argentina than PET. It's not the case for Brazil. PET is the mostly recycled plastic. 10% PP and 8% of high impact polystyrene. Around 2% of PVCs are recycled in Argentina. It's much less than in Brazil, where approximately 17% is recycled. And in general, the companies, they specialize in different steps or aspects of recycling. So there is one facility for collecting and separating. There is other facility for crushing and powdering, and some other facility for doing the pelletization. So there are many small and medium-sized companies or cooperatives throughout the country that are dedicated to collect and separate different types of waste, including plastics. And typically, plastic is collected and then sent to specialized companies in larger cities where the recycling facilities are concentrated. So final products made with recycled plastic in Argentina. So from PET, we have beverage containers, some cleaning products containers, textile fibers, and so on. For HDPE, we have domestic and condominium waste bags, various bottles and cleaning products, plastics, and also plastic wood. For PVC, most of it is used for pipes in construction or irrigation, and also as cable sheets. For LDPE, it becomes then plastic bags, pipes, plastic wood, films for agricultural use, and so on. For PP, also containers, crates, buckets, automotive parts. It's also the same for Brazil. Most of the PP recycling in Brazil goes for automotive parts. And for regarding polystyrene PS, it becomes some office items, trays, cornices, and shrinkings, and so on. So regarding those that are related to POPs, only 5% of the e-waste is recovered in Argentina. Most of the recycled e-waste plastics are not checked for POP contents, although Argentina is a country part of the BRS conventions. PVC is recycled within the country, albeit predominantly from industrial scrap, which means that the post-consumption PVC, as it has a low market value, is not really recycled. And approximately 130,000 tons of tires are disposed of in Argentina, and most of it is informally recycled into rubber granulates and sport cords and rubber tires. So they are not really used as fuel as in Brazil. But like in Brazil, most construction demolition waste is used for embankments and also not recycled, which means that they go directly to the environment. And 20 million of agrochemical packages are disposed of in Argentina every year without proper environmentally sound management, as they have no legal regulation for dealing with this kind of waste. So the last country regarding Chile, in Chile only 8.5% of plastic is recycled per year, which is equivalent to almost 9,000 tons. And it's distributing 17% that at the household level and 83% at other institutions or facilities or companies for the industry, let's say. And the most recycled type of plastic is polyethylene, is PET, followed by PE and PP. So it's similar to Brazil. So Chile also has a high collection rate of waste. And plastic, it's less, the plastic share is less than in Brazil, and in Argentina, it represents only 9.4%. But also most of the waste management goes for landfills, and 20% with a high share goes to sub-regulate the landfills. So only 48% of the installed capacity corresponds to grinding and 57% to pelletizing plastic waste. 83% of the pelletizing industry and 79% of the grinding crushing industry are located in metropolitan areas, like in Argentina. And in Chile, there are a total of almost 8,000 facilities to formally manage the different types of waste, which are divided into green points and clean points for that waste collection. And the Chilean government considers Chile Basura Zero, Chilean Zero Waste Program, as part of its official circular economy program, creating regulations and promotion that allow for recycling, proper waste management, and citizen involvement in achieving the goal of the country. So here we have the demand of plastics in Chile by polymer resin type and demand of plastic in Chile by the sector industry. So most of it is also used for packaging. And finally, the plastics that are related to POPs in Chile, if e-waste is recycled. No, in Chile, e-waste is recycled, but only 3.4% of this waste is collected and treated properly. Chile is part of the initiative called Strengthening of National Initiatives for and Improvement of Regional Cooperation for the Environmentally Sound Management of POPs in Waste, Electrical and Electronic Equipment in Latin America countries. The e-waste project is promoted by the Chilean Ministry of the Environment and the UNEP. And in Chile, the management of construction and demolition waste is recently being discussed, especially rubbishing and its reuse, but the issue of plastic has not been mentioned yet. So it's something that's going on right now at the moment. However, on May 2016, the Recycling and Extended Producer Responsibility Law was enacted, which essentially makes the manufacturers and importers of 6 priority products to recover a percentage of them once they end their life useful. And when they become waste, within this law, it's also wanted to manage building and construction waste. So regarding our sampling for the GMP, the UNEP GMP projects on POPs in plastic pellets, we did some effort with some colleagues in Brazil, Chile, and Argentina, where they went to some recycling facilities, and it was a little bit complicated to convince the recyclers that to give us some samples. Some of them were very happy when we explained the situation regarding POPs. Others were not so happy and didn't want to continue the conversation, so they just sent us away. And here is a table with the polymer types and the number of pellet samples that we have sampled in each country. We managed to get a total of 39 samples for Brazil, 25 for Argentina, and 25 for Chile. And again, the flow that the plastic recycling takes in the 3 countries, it makes it challenging for sampling because we only had access to the informal sector. So those that were the intermediary facilities where they would sometimes process the plastic waste and from waste pickers or some other cooperatives, and sometimes from industrial waste and scraps and make some pellets there. But most of them, they sell the pellets. They don't produce anything after it. They sell the pellets for other companies. And we had no access to any e-waste recycling facility. All of them were very close, and it was very hard to reach them for trying to get samples. So thank you very much for your attention. Here's some of the pictures, some PET recycling in Chile, some pelletization of PVC going on in Brazil, some e-waste regularly disposed of, and that's it. So thank you very much.
Thank you very much, Yago, for your presentation. One question. So for your countries, are you aware if there is kind of regulation from the government, what kind of polymers, recycled polymers can go to food contact materials, and what kind of materials cannot go to food contact materials?
I know for Brazil and Chile, I'm not sure for Argentina. For Brazil, we have some legislation from the government that only PET that was previously used for food contact material can be recycled into food contact material. And this is the same for polystyrene, the EPS and XPS. So they can only be recycled into food contact material if they had been previously used for that purpose.
Okay, and are you aware if there is any monitoring campaign from the government on such recycled pellets?
No, Roland, I'm pretty sure we don't have.
Okay, so there's one question regarding plastic recycling at Brazil, Argentina, and Chile. Is there any evidence where plastic credit in issuance project by Vera through verified carbon standards?
I didn't understand the question.
Yeah, but probably only if you know it. Do you know verified carbon standards? No.
Yeah.
Yeah. So they ask if
I'm
Brazil,
not
Argentina, or
I'm not
Chile,
aware about it.
if there is any evidence. No.
No,
So I think
I'm not
we
aware.
can check. We can check, and then we can show this later.
Mhm.
Then there was one comment. I sent 6 samples from Colombia taken from formal e-waste recycling companies. Why are they not recycled in our result reports? This is the reason. There are 2 projects. One is our project, which and we covered actually Africa and Asia, and Yago also sampled in South America. And there is a second monitoring project also in this UNEP GMP frame. This is organized by a Spanish laboratory, Dr. Esteban, and he is sampling also in other countries in South America. And your samples from Colombia are actually in that sampling project. Yeah, and so these are, let's say, two different project parts. And for our webinar, we only had this webinar in our project part, and therefore we have not mentioned the Colombia samples, but the data finally will go in one report. And so therefore also the Colombia data finally will be in the UNEP GMP report on screening POPs in plastic pellets. Yeah, so at the end, things will come together. Then there was one question about if the presentations will be shared. Yes, we will ask to the presenters for sharing the presentations, and they will also then come on the website of IPCP. Then, in addition to the recordings. Okay, are there other questions? No, not at the moment. So please be aware that Anna has shared a range.
Actually, there was a question, I think.
Okay.
There was a question earlier about sharing the report or the links to the report.
I will share it here in the chat.
Okay, that would be great. That was for the Argentina, but if you have other links, that would be great.
It's right here. Sure.
Okay, yeah. And we have, after the break, more...
And there's one more question. What's the name of the other project, which has Colombia information?
Okay, I mean, that's also in the frame of the UNEP GMP project. Yeah, so I think there is not a particular name. I mean, we can ask to Esteban. And as I said, this will be finally combined within one report. Yeah, but we will check. We can check with Esteban if there is a special name of that project. Yeah, and that project had another approach. So they invited then some people from laboratories from South America and made some hands-on training on PFAS analysis of plastic pellets in Spain. And at the moment, actually, I think 11 participants from different South American and GRULAC countries are in Spain to look for some hands-on training. Yeah, while in our project, we decided that a webinar will be useful to make a good outreach on the topic. And therefore, let's say these 2 projects are also kind of a bit complementary. The next presentation will be from Professor Innocent Nnorom from Abia State University in Nigeria. Professor Nnorom does since more than 15 years research on e-waste related issues, and in recent years also on broader plastic issues. So his presentation is also within our UNEP GMP project on sampling plastics recyclates in Nigeria and information on recycling situation. Yeah, Innocent, the floor is yours. I cannot hear you. No, you need to unmute you. Wait, unmute the microphone.
Thank you. Can you hear me now?
Yes, yes, very well.
Yeah, good morning, good afternoon, and good evening. It's actually afternoon here. I will be presenting the situation with sampling in Nigeria, and I will also be providing information on the recycling situation. Okay, so in our earlier research published in 2019, we reported that Nigeria has the second highest primary plastic import from all the 54 countries in Africa, only second to Egypt. So large quantities of plastics, polymers of different types are imported annually, and oftentimes also in products. And our person import project also showed huge quantities of plastic materials imported with electronics, either as electronic components or as household goods mixed with electronics in the containers during importation. So our study projected that the importation of plastics and polymers can only but continue to increase unless there are changes with respect to policy on importation and consumption of plastics in the country. Okay, so in Nigeria, plastic waste is actually a visible problem. One can actually see plastics, especially single-use plastics and PET plastics, commonly referred to as PET by stakeholders here. One can actually see them littering the streets and also drainages. It is estimated that about 32,000 kilotons of solid waste is generated in Nigeria annually. And about 2,500 kilotons of plastics is produced annually. And this is not properly managed in the country. About 8% of these 2,500 kilotons, that's about 200 kilotons of plastics, are discharged into the Atlantic Ocean annually. So this is actually huge quantity of plastics going into the ocean annually in the country. So Nigeria is currently ranked among the top 20 contributors of waste plastics to the oceans annually. So the reasons are obvious. There is poor litter abatement in the country. The municipal waste management system in most states are poorly run. And there is also poor implementation of existing frameworks, such as the National Policy on Solid Waste Management, and also the National Policy on Plastic Waste Management. Both were approved by the federal government in 2020. Most consumers are not aware of the dangers posed by the inappropriate disposal of waste plastics. So during shopping, one can see a consumer exiting a shop with 3, 4, or 5 different bags, poly bags, single use, that will be disposed in the next few minutes. So the situation is such that there are no official data in the country for plastic consumption. Quantities imported, quantities put on market, plastic waste generated, amount collected, and official amount recycled. One stakeholder told me that only 1 out of 5 PET bottles used in the country is recycled. However, presently, the Recyclers Association of Nigeria is making efforts to compile data for various recyclables, including plastics, metal, and paper. So the supply of recycled plastics to meet demand in the country is estimated at only 6%. So the rest are disposed with municipal waste at open dumps. There is therefore a large gulf between the growing demand for plastic and the supply. Infrastructure for collection, pretreatment, and recycling of plastics is not enough, and there is inadequate supply of materials to existing recycling facilities in the country. Most of the facilities operate in the informal sector. Some waste plastic types are not recycled in the country, either because there is poor demand for such materials, or the recycling facilities to treat such plastic types are not available. The sector is dominated by the informal operators. They are the ones that initiate collection, and they also supply materials to the formal recyclers. So available information shows that there are tens of thousands of informal collectors all over the country, picking waste plastics from dump sites, walking the streets to collect plastics, and then sorting them and then supplying to the recyclers. So in the pictures here, we can see materials collected and stored by the informal collectors. This is actually a collection center. We can see the baling process of plastics, and thereafter they are supplied to recyclers. Presently, only 10% of plastic waste generated in the country is recycled, according to the National Bureau of Statistics. And as I said earlier, majority of the waste plastics end up at open dumps or into the water bodies. So here, the recycling process involves collecting the plastics, sorting them according to plastic type, sometimes color also, cleaning them, shredding, melting the plastics. Sometimes they produce pellets, especially the formal operators. And then the pellets are then used to manufacture new products. However, the informal operators do not bother to produce pellets. They use the shredded materials to produce new products directly. The formal operators mostly depend on virgin materials. You can see the facilities, some of the facilities in the country, formal recyclers, some of the facilities. Sometimes, most often, they depend on virgin materials. Some facilities also mix virgin materials with some recycled materials. So the most commonly recycled plastics in the country include the PET, HDP, LDP, polypropylene, and PVC. Even though PET is recycled in the country, food-grade plastic PETs are not currently being recycled in the country. Most PET materials are used, recycled PET materials are used to produce other items other than food-grade materials. However, recently, the government licensed a facility to commence the recycling of food-grade PETs. Currently, the company is installing facilities and is yet to commence operation. So most recycled PET waste plastics are used to produce other materials, including straps or fiber materials that are then exported. The informal plastic recycling sector dominates recycling of waste plastics in Nigeria. However, the sector is not regulated, and the operators focus more on the profit. They are not interested in data collection and preservation. They are not bothered about their health and the environment. they try as much as possible to avoid the government and the government agencies. So they usually go into the rural areas and install their facilities, such that the government agencies will find it difficult to locate them for monitoring, enforcement, taxation. So the informal sector handles mostly collection, sorting of the waste plastics. Most often they do not produce pellets. They rather use the shredded materials to produce new products. The plastic materials that they do not use or the waste resulting from their activities are usually dumped around the facilities. And they also have some sieved out waste plastics that are often mixed with metals and other contaminants, which they often dump around them, and the locals use such materials to either light their cooking, their stove, cooking stove, or for cooking. They often depend on migrant workers to sort the plastics and do the pre-processing. So the sampling in Nigeria considered recycled pellets and shredded materials from the formal sector and also the informal recyclers. So here we can see pictures showing activities of the informal sector. Here we can see the plastic materials received. They handle electronic waste plastics, and they also handle waste plastics from end-of-life vehicles. So the materials are dumped here. You can see houses located around them. Then they take time to sort the plastics according to the polymer type. Here you can see sorted plastic stored according to plastic type. Thereafter, the materials are crushed. Here, oftentimes they take the risk of using their hands to force the plastic into the crushing machine. After crushing, they take time to sieve out the tiny particles of plastics which they do not want. That also contains some metals. So we can see only one person wearing a face mask or nose mask. Most others do not bother to wear personal protective equipment. So the sorted materials are stored either according to polymer type or according to color. Thereafter, the materials are then poured into the hopper and then used directly to produce finished products. So here we can see the product. This is a container used for packaging grease, vehicle grease. So they produce mostly non-food grade materials, containers, used often either for packaging vehicle materials, products, or for making motorcycle parts or other vehicle parts. So here we can see electronic waste components also mixed with plastics from end-of-life vehicles. So usually they focus on HDPE and low-density polyethylene. Before now, there was a recycling facility in Lagos that handled electronic waste plastics. The facility is now closed. So what they were doing, they focused more on crushing the wee plastics and then mixing them with virgin polymers to make chairs. So during monitoring, the Lagos EPA noticed the recycling of wee plastics, and they had to do awareness amongst recyclers in Lagos. So they visited recycling facilities in Lagos and educated them on the implications of mixing wee plastics with other materials and using such to produce food-grade materials. So they took their time to emphasize that wee plastics should not be used in making food-grade materials. However, the recycling facility has closed since. So The informal sector focused mostly on the black or dark plastics in the interiors of vehicles or from the engine. So the collectors take their time to visit mechanic villages around the town and collect these plastics, sort them, and supply them to the informal recyclers. So here we can see one of the operators sieving crushed plastics. So the materials here are often packed in bags and kept and allowed to accumulate. The villagers use this material to cook using locally fabricated stoves. Most of the informal recyclers are not aware of the dangers associated with the activities. They hardly use personal protective equipment, and they take unnecessary risks in their day-to-day operations. So they have poor work environment and no safety measures in place. There is a possibility of inhaling and ingesting the tiny particles during their day-to-day operations. There are no safety measures for fire around their activities. So they are more interested in the profit that they make. So we took time to collect some of this waste plastic material, and we sent this alongside the consignment that we sent to Japan to see the harm, the people using this to cook are facing. So for the sampling proper, the most handled plastic types in the country, as I mentioned earlier, include HDPE, LDPE, and PET. We also have some facilities handling polypropylene and PVC. Only few facilities handle HIPS and ABS. The collection centers and informal recyclers take their time to collect these two types of plastics, crush them, and allow them to accumulate before supplying to the few facilities that recycle them. However, there are other types of polymer types that we did not encounter during the sampling period, including low-impact polystyrene and polycarbonate. For the sampling approach proper, we made a list of former recyclers in some selected states in the country from a DEX study. After compiling the list, we consulted local waste plastic collection centers and updated the list because the local collection centers supply the plastics used by the formal operators. So we used their experience and contacts to update our list. Then we embarked on field trip to collect the samples, visiting the former recyclers in the various states. However, we encountered lots of challenges. Maybe to protect their business, most of the companies did not allow us to access their facilities. Oftentimes, the security personnel will have excuses not to grant entrance into the facility. For a few of the facilities that granted us access, on entering the facility, we'll be referred to the human resources manager. The human resources manager will refer us to the production manager. Production manager sometimes will refer us to the managing director. And in the end, we'll be asked to come back next week. On returning the following week, they would inform us that samples are expensive and in short supply. So in the end, we collected only few samples from the former recyclers. We now decided to do networking with friends, colleagues, present and former staff of plastic companies, former recycling, plastic recycling companies, to see if we can use them to gain access and collect plastics. We also use incentives and paid for most of the samples to make them to bring out the samples. When we adopted that approach, we were able to get few samples. It took quite some time before we got the samples. Thereafter, we networked with owners of waste plastic collection centers. Some of these collection centers have crushing machines. So they collect plastics, sort the plastics, clean the plastics, and sometimes they crush the plastics before supplying to the recycling facilities. So we approached them and used the contacts they have in the former recycling facilities to get some samples. Thereafter, we also collected some crushed materials from them, which they have accumulated to supply to recycling facilities. To be able to get enough plastic materials used in packaging foods, we also requested that they crush some selected polymer types and products for us. So they obliged us and crushed the plastic materials and supplied to us. So working with the collection centers enabled us to have a good supply of plastic materials. We also liaised with informal recyclers. We approached them in the rural areas where they are located and had some discussions with them. They welcomed us and granted us access to their facilities. They volunteered samples willingly, and they allowed us to take pictures and make videos. So we also used the opportunity to create awareness, discussed with them the health implications, the risk they are taking, and they really appreciated the visit. Along the line, we also discovered an open market for waste plastics. The market is patronized by the informal operators. So the collectors collect plastics, sort them, and display them for sale. Here you can see some of the plastic materials displayed for sale. The informal recyclers come here to buy materials. Sometimes after pre-processing, they also supply to the formal recyclers. However, we didn't get any samples from this market. So here we can see the market. You can see bags of plastic materials displayed for sale. It's mostly from vehicles and some electronic parts. The samples we collected are used for household goods. We also collected materials used in making vehicles, waste plastics from vehicles, collected plastic materials from electronics, and then we also collected the debris, the waste from the informal recyclers that is used for cooking by the locals. So these are the samples we collected. So many of the recycled plastics or pellets we collected, at least, some of them are partly used in food contact materials. So the materials collected includes pellets, shreds, virgin materials, and waste materials. We collected HDPE, low density polyethylene, ABS, general purpose polystyrene, polypropylene, PVC, and HIPS. So these are some of the cities that we collected samples. So here we can see pictures of the crushed materials we collected. So even though they are not educated, they have a means of identifying the different polymer types. So even though we can see that there are different many colors here, the informal operators take their time to sort them according to polymer type before crushing. Here we can see recycled pellets collected from former recyclers. And here we have virgin materials that were collected from former recyclers. So we collected about 115 samples, mostly shredded materials, and also pellets, and then virgin materials. We made a list of information from the sampling process: the polymer type, the sampling location, the sampling dates, the pellet origin, the pellet feedstock application, etc. The color of the pellets. All these information were compiled in Excel sheets and then sent with the consignments to the various laboratories. After sampling, the plastic materials were packaged, and then we shipped them. It took quite some time. We tracked the samples as they moved, and then the samples were delivered to the laboratories in Germany, Spain, Japan, and the Netherlands. Thank you for your attention.
Yes, thank you very much, Innocent. And no, not only for the presentation, but really for your effort. I mean, what you heard here in this presentation, sampling more than 100 samples in Nigeria, was really a challenge. And also, I mean, the slide on the shipment of the pellets, right? For example, to Japan, it took more than a week to find the right company and so on. So thanks very much. Maybe one addition, I think, which you did not present. You told me that you also found that some of the shreds which were not recycled are used for heating purposes. Maybe you can elaborate a little bit more on this.
Yes, I talked
also for other countries. Yeah.
Yes, I talked a little about that.
Yep.
The waste plastics that are sieved out by the informal operators are stored within the facilities. The locals come and take huge quantities of these plastics. And because they are flammable, they use them to light a fire before adding other combustible materials. However, some of them use only the waste plastics for cooking. They use locally fabricated stoves, and they do the cooking sometimes inside their homes. So this is one of the reasons why we had to collect some samples from some of the informal operators and included them in the consignment that we sent to Japan, so that we can evaluate the risk from using such by the locals.
Yeah, thanks much. You can stop sharing your screen, and then we come to the next presentation. The next presentation is Dr. Nudjarin Ramungul from the National Metal and Materials Technology Center, MTEC, in Thailand. And she will present on sampling plastic recyclates in Thailand and information on the recycling situation in her country. Yeah, Nudjarin, yes, we can see your slide. Now
Okay.
you can go to presentation mode.
Yes.
Yes.
Okay.
Super.
Yes. Good afternoon. It's the. That's me. Oh, sorry. Okay.
Presentation mode.
Okay. Okay.
Yes.
Good. Good morning, good afternoon, and good evening, everyone. Today I will present about the samplings of plastic recyclates in Thailand and information about the plastic recycling in Thailand. So, introducing to you a little bit about my institute. We are the National Metals and Material Technology Centers, a government-owned institute. We are almost 40 years old now. We are working on the research and developments on the material technologies. We have together right now 7 research group aligned toward the basis materials, ceramics, polymers, rubbers, and metals. And we are also have 3 cross-cuttings research group: design engineering, biomedical materials, and for me, belong to the environment research group. To give you an overview about the plastic value chain in Thailand, I will present you this a little bit messy diagram, but I compiled all the relevant data here. We have the petrochemicals industries. We have feedstock also from bio-based agricultures. In Thailand, we have resin producers with a capacity of about 9 million tons a year. And we have about 12 companies with about employing about 50,000 jobs. The resin producers also import and export resins. We import about 2.3 million tons and export about 3.3 million tons. The resins are sent to other companies called compounders. We have about 110 compounders in the countries. The compounders receive the materials from resin producers and also from traders. And they also have mostly import additive from abroad as well. We have about 120 additive suppliers. After compounding, the compound resin are sent to converters. We have roughly about 2,000 converters who converts about 5 million tons every year for producing plastic products. The products itself can either send directly to the users or sent to end products producers like electrical and electronic industries, the vehicles industries, and others. We also import plastics indirectly from products, and also products producing from end product producers also export. But roughly we import more than export. At the user side, when the products has reached end of life, they have roughly 2 to 3 methods to dispose their products. One of the most famous method is to selling them to what we call it a selling, a tricycle, buying workers who calling to the home to sell their unused products. For this, we estimated that there will be like about 1.5 million jobs in these collections paths. They are mostly informal. The users can also throw the plastic waste to the garbage, which will be the job for the municipalities and the local authorities to collect. And for those users who do not have facilities nearby, they can also sort to open dump or to open burnings. That's after the municipal collect the samples, or after the selling by the materials, they will sell it. They will sort it and sell it to what we call it the recycle shop. But these are not really a recycle, but they are buying back the materials. The materials bought back will be sent to dismantler and then to the regional recycle shop, the biggest collectors within the region or within the northern part or the southern part of the countries. We estimated that there would be like about 30,000 companies working in this group. Once the materials reach the regional recycle shop, the recycle shop can decide to sell it to large recyclers or sell it to small sorter companies. So right now we have roughly about 15 large scale recyclers in the countries. These large scale recyclers produce fibers from PET or post-consumer recyclate and send it back to converters or to compounders. As for the large scale recyclers, they have all the equipments. For example, the NIR, the sorters, the decontamination, all those kind of industrial size, industrial recycling facilities should have. As for the other part, for the smaller waste processors, we estimated that we have like about 400 companies. These are those mostly informal companies. They do manual sortings, do shredding, and doing the washing and cleanings. And within these facilities, they might also doing the sink and float to further sort out the materials. The sorted materials then sent to what we call the small scale recyclers. These are mostly, we call them the specialists, in the sense that they are very different from the big company, the large companies, in the sense that they accept almost every type of the materials, and they either compound the plastic and send it to converters, or send the materials as is to the compounders. Some of these PCR, the post-consumer recyclates, also export. I have to mention also that some of the pellets, the plastic scrap, are also imported from other countries. And the residue from the waste processors will also going into the landfill, open dump, open burning, or it depends on where they are located. What are the facilities close by. They can even send it to the waste to energies, send it to incineration as well. As for the compounders and converters in Thailand, we have like about 300,000 jobs. So Thailand actually have initiated the ban for the import scrap, and then we run into problem of the shortage of the scrap. So Thai industries, the government decide to allow it to phase down, but to be completely ban the import scrap by 2025. These are the application of the plastics that are produced within the countries. There's mostly PP, HDPE, LDPE, polystyrene, and PVC, PMMA. The materials will mostly go to packaging, automotive, electronics industries, houseware, construction, and others. I like to mention here that for most of the statistics we have within the countries, mostly for the packaging portion. There's durable products. For example, automotive, electronics, and also the construction, which account for about 40% of the market share for these durable products, when you produce it every year, it will not come out for within that year, but it will accumulating. So the data will it will be stockpiled within the house or embedded in the products. In Thailand, we have only 2 registration to controlling chemicals in products. One is the food contact materials. In Thailand, the food contact materials will have to only produce from virgin materials. And only last year that the government allowed the use of recycled materials for the food contact for the food contact containers. But for this, there will be approved. It will be approved in case-by-case basis. And currently, there's only the PET has been approved. We also have standards for the Thai rules standards, but this is pretty much the same as EU rules, except that this is the voluntary standards. In 2021, the World Bank has done some studies for Thailand and estimated as only 18% of the materials are recycled, and the rest are not recycled. And we waste about 2.9 million tons. But I'd like to address that these 2.9 million tons account only for the non-durable products. These are the overview of material flows for the material studies conducted by WWF. Again, most of the materials are bags, containers, bag, bottles, and others. And the rest for the durable products are pretty much not covered, and or they are very hard to trace. The end of the products, they are only like about 500 kilotons or 500,000 tons are recycled. The rest are going into the landfill or into the incineration. Characteristic of Thai plastic materials are we have long history of buyback system, but we have weak control of material coming in and also the pre-market stage. So we have very little control of the substance embedded within the products. We have very weak end of use and end of life management. So we are very much lack of comprehensive collect back system, and that hinders our recycling and disposal practice. And I think like everyone, we lack of data. I'd like to show you a little bit about the flows of the materials. We have these are the buyback system. This is the materials collected and drive into to sell the materials. The materials are collected based on the applications and sorted based on colors and also based on the resin, crush it, wash it, and dried it, and then pack it. Mostly, most of the time, the materials can be used as traded materials, but also sometimes the materials are also produced as pellets. The mainstream that we produce are mostly right now PET bottles, because of the law allowed the bottles to come back as food contact materials. But before this, they are recycled from bottles into fibers. Polyolefin, PE and PP, both rigid and firms. Styrenes, we have HIPS, high impact polystyrene, general purpose polystyrene, and ABS. There's also ABS V0s, stand for the flame retarded grade, and also HIPS V0s, flame retarded grade, which in fact can get higher price than general purpose materials. General HIPS, general ABS, and general polystyrene. We also recycle rigid PVC, and they will be shredded into chips and further shred down into powders. We also recycle soft PVC, and for soft PVC, they are collect and clean and sell like this because there is no need for the process to make it a pellets. Also, we are also recycle plastic PVC, flexible PVC, flooring and shoes. And these are the pellet samples we sent to the projects. For this, we collect from 17 shops. It has been hard as well to find the pellets and also to find the shops that willing to collaborate with us. For this 17 shops, we can get both PCR, PIR, and also mixed PIR and PCR. And within these pellets, 40 samples are tested high for bromine. For Thailand, we identified that there's we really now would like to produce high quality recyclates, but we run into a problem about the contamination, and the legacy additive, the embedded additive will be the biggest barriers for us. And the products itself is also has not been designed to aid the recyclings. The design of the products, designers right now, they are pretty much aware of the problem, and they are trying to design products to fit the circular industries. But the design itself has not been checked, and also it has not been compatible with the recycling industries. And we do not have technical capacities or competency to trace the materials. So we think that there's 3 keys to success. One is the transparencies. As everyone can see that these industries are not quite transparent, and the products itself, the materials has to be traceable, and the user will have to trust the materials. And these 3 properties are not there yet for us. In summaries, for Thailand right now, we roughly consume about 5 million tons. The materials that reach end of life, maybe about half, 2.5 million tons a year. We have a capacity to recycle about 0.5 million tons right now, but we estimate that about only 10% of this are good enough to be recycled into the high quality materials. The high qualities in this sense, we characterize it as transparent, traceable, and to be trusted. And we estimate that within the current circumstance, the demand for the high quality materials will boost up, and the supply will catch up in the near futures. And that's it for me. Thank you very much.
Yes, thank you very much, Nudjarin, for this very good overview presentation. Yeah, happy to see, I mean, how well developed the plastic recycling industry is, and also that your institute is looking into details. Because the next 2 presentations will be on the monitoring, maybe I would like to take this, finish after the 3 presentations about the pellets. We finish the topic of this plastic sampling and recycling overview of countries. I would like to take a question on this topic. So here to Innocent. So why did the Lagos facility closed? Was it rather lack of market for the chairs, environmental issues? Yeah, Innocent, I don't know if you know anything about the status and the reason why the facility has closed at least for the time being.
Okay. Yeah, can you hear me?
Yes.
Yeah. My contact person at Lagos State EPA, one of the reasons she mentioned is that it appears the products of mixing WEEE plastics and other plastics to produce chairs, the products were having issues and the demand for the products declined. So the company was not making profit and they had to close that particular facility. They are actually into other polymer types, but they stopped using WEEE plastics.
Okay, and another question again to the cooking materials. Do you know a bit more detail on these waste materials used for cooking? These plastics, or is this rather just all plastics people can get?
Please come again.
Yeah, so there's another question. What type of waste materials are used for cooking materials? I mean, the plastic ones, yeah, if you...
Okay, a mixture of the waste plastics generated by the informal operators are used. The focus is on flammability, ability to catch fire and enable them to cook. That's their focus. So they do not bother whether the plastics are from electronics or from vehicles or from other plastic sources.
Okay, yeah, thanks. Then there was one question, may I ask where these samples go to and what information to get? So this is rather on the project. So yes, I mean, we have 4 laboratories which are doing screening. So samples, like Innocent showed, were sent to Germany, to Fraunhofer Institute, to Japan, to National Institute of Environmental Studies. Also in Thailand, Dr. Ramungul is doing some monitoring. We have bioassay laboratory in the Netherlands doing some screening, and the Spanish laboratory from the other project is doing also some screening. The Spanish is looking for PFAS. The Japanese laboratory is looking for brominated flame retardants and chlorinated paraffins, short chain and medium chain and long chain paraffins. The German laboratory is looking for UV stabilizers and Dechlorane Plus, and the Netherlands laboratory is looking for toxicity. And by this, I just come to the next presentation, because this is from Dr. Natsuko Kajiwara from the National Institute of Environmental Studies. So where all the samples are shipped, and she will tell about the first step of the assessment, which is screening of brominated and chlorinated additives in plastic pellets to recycle the products made by the recyclates. Is there a project monitoring how is treated those products at the end of life? Yes, I mean, recycled products can be recycled again. For some plastic, this works fine. Polyethylene, polypropylene over time get oxidized. This means the chain lengths get shorter, the quality gets less. So this makes a limitation of recycling on long term. And the second question, is there a project monitoring how is treated those products at their end of life? No, at the moment, this is not part of our project. We really like to fill the gaps of monitoring POPs in these recycled plastics, where I said before that there is actually only, let's say, one larger study out on looking on POPs in recycled plastic. So the end-of-life assessment of other products is not a topic of this small project.
First of all, I would like to thank Professor Martin Scheringer and Dr. Roland Weber and the organizer of this webinar for inviting me to talk here today. My name is Natsuko Kajiwara from National Institute for Environmental Studies, NIES Japan. Today, I would like to share my experience regarding a screening method of POPs used as plastic additives by using a handheld XRF analyzer, as described in the guideline document mentioned by Roland in the previous presentation. This is a brief outline of my presentations. First, I'd like to give a brief introduction. Next, I'll talk about XRF screening of bromine chlorine contents and some case studies applied to plastic samples. Then I will touch a little bit about ongoing project on recycled plastic pellets. As already explained, most of the newly added POPs for global elimination are plastic additives. And some of them are brominated compounds, and such as PBDEs and HBCDs, and some of them are chlorinated additives. This slide summarizes the chlorinated and brominated POPs used as plastic additives. They have been widely used in a variety of plastic products. Concentrations in treated products are usually the order of percentage as shown here. To promote the recycled plastic for circular economy, it is necessary to eliminate plastics containing POPs from the recycling streams. However, it is time-consuming and expensive to measure each compound by chemical analysis. So it is effective to quickly screen the content of bromine and chlorine plastic products and waste by XRF as indicator of the presence of POPs, and select samples to be further confirmed by chemical analysis. XRF is a non-destructive analytical technique used to determine the elemental composition of materials. XRF analyzers determine the chemistry of a test sample by measuring the secondary X-ray emitted. This one from a test sample when it is excited by a primary X-ray radiations. Each of the elements present in the test sample produces a set of characteristic fluorescent X-rays that is unique for the specific elements. It is why XRF spectroscopy is a good technology for qualitative and also quantitative analysis of elemental composition of a test sample. I'd like to emphasize that to screen the elemental composition in plastic samples, the measurement time is typically as short as 30 seconds. So we don't need even 1 minute. So it's very quick. There are a few things to keep in mind when using handheld XRF. The sample should completely cover the measurement window of the devices. Number 2, in the figure on the left is a measurement window. It's about 1.5 centimeter in diameters. So sample should be bigger than this window. And the second, the sample should be homogeneous. And the sample should be thick enough that additional material will not affect the result. For plastic samples, the thickness should at least 1 centimeter, or the area to be measured should not be in contact with any other materials. And fourth, this is very important, that XRF analysis is limited to the detection of elements, including bromine and chlorine in the test samples, without any capacity to identify the type of additives. So, for example, TV casings shown here is very easy to analyze by handheld XRF, even outside, because the plastic part is very big enough and it should be uniform. And handheld XRF is very light, so you can bring it back to outside and can use outside also. On the other hand, the plastic waste is often generated as shredded mixed plastic like these pictures here, but it is very difficult to measure the average concentration of bromine and chlorine in such shredded materials by XRF as it is. This slide shows the result of validation of accuracy of our previous handheld devices. The screening was conducted with rose-green mode as shown here, and analytical time was set at 30 seconds. Target elements of this study are shown here, the 5 elements, and we analyzed 4 different types of polymer reference samples: P low, P high, PVC low, and PVC high. And these polymer reference samples has the certified values as shown here. And compared with concentration obtained by our own devices. These are our data from my devices. As shown here, our data were comparable to the certified values and sufficiently accurate and stable to be used. Well, our target compounds to monitor bromine are PBDEs and HBCDs. The bromine concentrations obtained by XRF is not directly the concentration of PBDEs or HBCDs. I put the chemical structure, molecular formula, and molecular weight of PBD209 and HBCDs in this table. And the chemical composition indicates that PBD209 and HBCD have bromine contents of 83% and 75% respectively. So this means, for example, if the bromine concentration measured by XRF was 1,000 milligram per kilogram by weight, and if all the bromine were divided from PBD209 HBCDs, it corresponds to 1,200 milligram per kilogram of PBD209 and 1,300 milligram per kilogram of HBCDs, respectively. Conversely, for example, if you want to ensure that PBDEs and HBCD concentration are below 1,000 milligram per kilogram, bromine concentration should be below 830 milligram per kilogram and 750 milligram per kilogram, respectively. As I mentioned earlier, XRF cannot distinguish the type of brominated film retardant present in analyzed sample materials. I listed some of them here. Many unregulated brominated film retardants are currently in use, and even if bromine is detected in test material, it does not necessarily mean that it comes from PBDs or HBCDs. But still, screening with XRF has advantage of greatly reducing the number of samples actually performed for detailed chemical analysis. Next, how about chlorinated compounds used as plastic additives? Chlorine can be used as an indicator as well as same as bromine. I would like to mention here 2 different points from bromine. The first one is about the detection limit. The limit of chlorine concentration in XRF measurement is several orders of magnitude higher than that of bromine. Of course, it depends on the sample materials to be analyzed, but in general, bromine is detectable in plastic at around 5 milligram per kilogram. But chlorine is not detectable until it is at least 1,000 milligram per kilogram. The second point is, especially for SCCPs, the main application is as a plasticizer for PVC, but PVC already contains a large amount of chlorine, up to 70% by weight. So it is difficult to determine the presence or absence of SCCPs or Dechlorane Plus based on the XRF screening of chlorine concentrations. But XRF screening may be effective for polymer products that do not originally contain chlorine. But we need to accumulate case studies of such case in future. As I explained here briefly, the XRF screening has its advantages and also limitations. But if we keep them in mind, I believe it is a very useful tool for all of us here today. Next, I'm going to introduce some case studies applied XRF screening to plastic samples. This is a case where XRF screening was applied to review unintentional PBDs contamination of new products due to recycling. We collected a wide range of small plastic items, totally 540 products, and more than 1,000 components after dismantling, including these children toys and other consumer products purchased in Japan and 17 other countries. All the samples collected were dismantled to each component, and bromine content was screened by XRF. So we analyzed more than 1,000 samples by XRF. Then the samples with bromine contents more than 30 milligrams per kilogram were pulverized, ultrasonically extracted, and PBDs were analyzed by GCMS-MS. These three pie charts showed how many samples each had bromine detected in these concentrations and ranges. These pale blue areas had low bromine concentrations, less than 30 milligrams per kilogram, and they are unlikely to contain bromine-free retardants above the Basel Convention LPC. So we omitted these samples for further chemical analysis and selected 219 plastic components. That's about 20% of the original samples, contain bromine at a concentration of more than 30 milligrams per kilogram. This means that 80% of samples can be omitted from the detailed analysis. So XRF analysis is very useful for pre-selecting samples for detailed analysis. And for these 219 samples, after pulverizing the samples, we conducted PBD analysis by GCMS for confirmations and also more accurate bromine determinations using combustion ion chromatography. I'll show you the result of bromine contents analyzed by using CIC first. It was not always possible to pulverize the exactly same part of the sample where the XRF measurements were actually made. And there was also a possibility that the bromine concentration in each component was not really evenly distributed. But a clear positive relationships was found between bromine concentration determined by XRF. This is a non-destructive technique, so this is a data before pulverizing the samples, and those measured by combustion ion chromatography, CIC, which is more sensitive than XRF, but also we need a destructive procedure. So I mean, after pulverizing the sample, we can use a CIC technique. And chemical analysis of these bromine positive components of PBDs revealed that among more than 200 samples, 109 pieces, that means like 10% of the total samples, mainly those made of black colored plastic, contained PBDs at concentrations ranging between 35 to 10,000 milligrams per kilogram, with the maximum contribution from DECA-BDE. These PBD concentrations were not enough to impart flame retardancy, suggesting that the recycled plastic used to manufacture these consumer products probably originated from e-waste. This slide shows the relationship between bromine concentrations and PBD concentrations for the bromine positive samples. If the detected bromine concentrations in the component originated only from DECA-BDE, the plot would appear on the dashed line in the figure, this one. However, all plots were below the dashed line. So it means that none of the bromine detected in the samples could be explained only by the presence of DECA-BDE. This finding was attributed to the presence of other currently non-regulated bromine-containing compounds found in e-waste plastic, such as decabromidiphenylether or like tetrabromobisphenol A. In other words, the bromine screening is not 100% perfect indicator to distinguish PBD-containing products. In the next slide, I would like to show you another case study applied to shredded e-waste mixed plastic. As you can see, there is no clear relationship between bromine content and BD-209 concentrations again here in these samples. And most of the samples contain high concentration of bromine, up to about like 15% of bromine, clearly indicating that the BFRs were intentionally added to these products. However, they were not derived from PBDs. Please look at this blue diamond point. This sample is mixed plastic of CLT TV casing manufactured in 1990s, so very old TV casings. And this is the only cases that we can explain its bromine content by DecaBD usage. So I think it is imperative to develop a practical on-site method to separate BD-209 containing plastic from non-PBD plastic in the dismantling stage to obtain PBD-free plastic flow material recycling. Okay, then from the next slide, I would like to introduce some of data obtained from our ongoing project on recycled plastic pellet. So far, we received 269 samples from 9 countries in Asia, South America, and Africa. Also, we have some presentation from GRULAC countries, Thailand and Nigeria in the first half of today's webinar. And here are the pictures of some samples. Those recycled pellets include PEs, PPs, PS and ABS, and also we have some PET and PVC as well. As I mentioned earlier, the samples for XRF analysis should not be too small and should be homogeneous. However, as shown in the previous slide, the pellets are tiny, less than 5 millimeters in size. So we put them together in plastic bag like this and check the variation of bromine concentration when measured multiple times at different parts, like here, here, here. And as a result, the variation was sufficiently small, about 6% even for samples with low bromine concentrations. So we concluded that the plastic pellets could be considered homogeneous. And we follow the usual step to select which sample to be analyzed by GCMS. And this time we are trying to select a pellet sample with bromine content more than 50 micrograms per kilogram for PBD analysis. Next, I'd like to show you the tentative results from XRF screening of bromine contents found in the pellet samples. This pie chart shows how many samples each had bromine detected in these concentration ranges. So among 269 pellet samples analyzed, 195 samples had bromine concentration below 50 milligrams per kilogram. At this moment, we omitted these samples for further chemical analysis and selected these 74 samples for, that's mean that about 30% of the total samples contain bromine at the concentration of more than 50 milligrams per kilogram for further PBD analysis. And this is still ongoing project, and I have no further data to show you today. I'm sorry, but I think the next time I can show you some of my data. And that's all from my side. Thank you very much for your kind attention.
Yeah, thank you, Natsuko. Yeah, also you are probably already sleeping in Japan. I will then tell on the weekend. There is one question directly to the presentation of Natsuko. Could you share what were the reason to set the 30 milligram per kilogram bromine screening set point are related to the XRF devices? No, I mean, one is that the lowest low pop limit of the Basel Convention or proposed low pop limit is 50 milligram per kilogram. This means 30 milligram per kilogram is enough below that limit to safely are below the lowest proposed pop limit for PBDEs. You have seen that Natsuko also screened down to 5 milligram per kilogram, and also is analyzing some of the samples which are lower. Yeah, good. So then we come to the last presentation today. So this is an addition. So we just had the screening of bromine and fluorine, bromine and chlorine in the presentation of Dr. Kajiwara. The last presentation here from my side is on monitoring of PFAS in products and recycling, including screening methodology for fluorine in plastic, side chain fluoropolymer coatings, and other materials. It also links to the guidance, and I will introduce you to the guidance or to the PFAS part here of the guidance on monitoring of POPs in products and recycling. When we look to the 34 POPs listed in the Stockholm Convention, 3 groups of perfluoroalkyl and polyfluoroalkyl substances, PFAS, short PFASs, have been listed in the Stockholm Convention with hundreds of related compounds. For example, for PFAS, there are 165 related compounds. And a large volume of these precursor chemicals are so-called side chain fluorinated polymers. Also, we have the long chain fluorinated polymers at the moment in the POP reviewing committee for the assessment, and therefore PFAS will become even more important. The detailed link between listed PFAS and polymer and plastic has been described by Professor Ian Cousins in the webinar on 24th April, and there you can watch the recording of that presentation. So in his presentation, he showed the large PFAS universe, and a part of this PFAS universe are polymers. And from these fluoropolymers, the most interesting or the only interesting or the most interesting one for POPs PFAS are the so-called side chain fluorinated polymers. Because here partly POPs including PFOS or PFOA or PFXS have been used in large amounts in the past in those side chain fluoropolymers. So here, that's an example of a carpet surface which is a side chain fluoropolymer of PFOS, and this PFOS covered on the surface is covalently bond and can be hydrolyzed, and then so-called foci, these are PFOS precursors, can evaporate. There was a recent overview presentation on these side chain fluorinated polymers from Dr. Wang, and a report from OECD on these side chain fluorinated polymers, where he highlighted there are different polymer backbones, acrylates, urethanes, oxytanes, ethoxylates, and overall there he said there's a list of about 103 side chain fluorinated polymers, including 42 PFAS monomers in this OECD report. And when we look to their relevance here for PFAS, we see that historically many short-chain fluorinated polymers contained this long-chain PFAS, including PFAS. So, and that they have been produced in thousands of tons per year, which is at least one order of magnitude higher, for example, compared to the production of non-fluorinated PFAS like firefighting foams. So here you see the production, the use volume of PFAS in the European Union in 2000. 2000 is an interesting date because it was the highest production volume of PFAS before 3M stopped production in 2000, and production decreased by more than 90%. So here you see that from the about 500 tons, about 490 tons has been used here in surface treating, yeah, including fiber coating and paper. And these 400 tons are these side chain fluorinated polymers. Yeah, while when you look here, for example, to firefighting foams, the use per year was less than 1 ton. Yeah, so this shows the relevance of these side chain fluoropolymers also for PFAS. Over the last 20 years, many long chain fluorinated many long chain side chain fluoropolymers have been replaced by short chain ones, while some long chain ones may still be used. Yeah, for example, in Asia, there is still production of PFOA related substances used there. And therefore, it's quite relevant and also complicated to monitor those, because these long chain PFAS are covalently bonded. So how approach the guidance documents? Again, here, the step-by-step approach: first screening what kind of products, then sample collection, then screening and quantification. And in this presentation, I especially will come to different screening technologies. But as presented in the first presentation, the guidance provide also a survey of products, also here for POP PFAS, and the different recycling flows of PFAS. So important one is, for example, carpets, which have a long service life, but also textile with relatively long service life, and also with some recycling activities. I give you 2 examples. Here on end-of-life management of carpets and reuse and recycling, here from one website, which propose that the reuse of carpets in garden allotments. So here carpets can be used to reduce weeds in your garden or allotments. But if you do that, of course, PFAS can be released in the garden and accumulate in fruits and vegetables. So also that website proposes upcycling of carpets for compost insulation. So old carpets is perfect for keeping your compost insulated, but the same if the carpet release PFAS, they go into the compost and afterwards accumulate in your plants. Or here to use carpets upholstered for the headbeds or for bed and pillow cover. Also this includes and result in high exposure risk. So here the California EPA stressed the risk of such carpet recycling and reuse, but unfortunately up to now I have not seen any study of this. Yeah, so the more important we have in this guidance, a kind of guidance to screen for such PFAS in such reuse and recycling streams. A second recycling and reuse stream might be tents, which can be treated with PFAS to repel water. and also can contain hazardous flame retardants to reduce the fire risk. Hence, care is needed in the end-of-life management of tent fabrics. So again, here I have just highlighted some issues from a website, which is suggesting to repurpose and recycling tent fabrics. So the suggestion is here, with the tent fabric, line your child's school bag or arts and crafts. Cut old tents up for arts and craft. Let children express their artistic flair. As ground sheet, rather than restricting your children's access to carpet areas, use tent as a ground sheet. Tent fabric is a perfect barrier between kids and carpeting. So here both might contain PFAS, so the tent fabric and the carpet. Then make a table protector. If your drapery is a tablecloth, tent fabric is a good waterproof barrier. So by this, you directly can bring PFAS and flame retardants onto your table. Also, proposed as a mattress protector, which says nothing degrades a mattress more quicker than moisture. Fit your old festival tent fabric to your mattress before it fit the first sheet. So also here by this, you can then just get the PFAS into your bed and related exposure. And the worst one is the proposal of storage sacks for long-term storage of packed lunches. So also you see here there is high risk for this kind of PFAS treated material, and it should be assessed and avoided. But up to now, I have not seen a monitoring study published on such reuse and recycling. So therefore, when we look here to step 1, survey of products, I just gave you 2 examples. The largest amount of PFAS and PFOA side chain fluoropolymers have been used in carpets, textiles, paper, and therefore those products and related reuse and recycling of those PFAS containing materials are the first type of products to aim for. So sampling campaigns can be proposed either by governments, I mean, for the implementation of the Stockholm Convention. Yeah, it is useful to include that in the national implementation plan, for screening also of recycling cycles, or of course by research institutions, or in combination. But also the custom can play a role. You have seen that we have large material flows, especially of waste products to developing countries. And here, let's say carpets and textile can also be an aim of screening. So Annex 1, as presented in the first presentation, contain information of PFOS, PFOA, PFAS, and related compounds in products and recycling, and give some idea. Additionally, there are different criteria which can be used to screen for PFOS and PFOA. One are CAS numbers of products, for example, but what we have found is even for firefighting foam, often they are not labeled. And for carpets and for textiles, I have not seen that any of those have been labeled with a CAS number or the information of PFOS and PFOA. Then the product can be identified by certain properties. And this is a good chance, because here for this PFOS and PFOA and other side chain fluoropolymers treated products, we have stain resistance, water repellence, and anti-grease properties. So this is one approach to do a pre-sampling, yeah, on shops, for example. We have also compiled here in Annex 2 best practice case studies for sampling and screening PFOS, PFOA, and related compounds in products and recycling, where you can have a look at. And the next step is then the screening in the field or in the laboratory. And here the guidance give an introduction to screening approaches. This includes screening technologies for fluorine. So here screening minimizes the time and expenses of confirmation analysis. And such screening enables a relatively cheap and simple pre-selection of products with regards to their possible PFAS content, such as carpets, textiles, and paper, with fluorine as indicator of PFAS, including short-chain fluorinated polymers. So when we look here to the production age, because for PFAS, the main production has already stopped 2000, but the exemptions for PFAS for textiles and carpets, they stopped, or the use stopped around 2013. This means for PFAS products older than 2013 of textiles and carpets might still contain those, while for PFOA and PFAS and related compounds, they have been used until recently or are still used in these applications. The guidance lists more than 8 screening technologies, including droplet tests, sliding spark spectroscopy, NMR spectroscopy, and in the next slides, I will just go through those techniques and also explain a few case studies. So when we use screening of fluorine in field or laboratory, it needs to be considered that not all fluorine stem from PFAS. Yeah, so products also can contain, of course, inorganic fluorine. So that need to be distinguished. Also, when monitoring PFAS, not only the extractable PFAS need to be considered, but that a high share of PFAS might not be extractable in products due to the high share of this PFAS in the side chain fluorinated polymers. Yeah, this means here is a big question mark, and they are covalently bond. Therefore, with normal extractions, they cannot be extracted. On Monday, we will have a presentation on total oxidized fluorine assay, yeah, which might degrade a large part of this polymer. This will be presented by Professor Jun Huang from Tsinghua University. The first screening technology where I want to show some details is the so-called droplet test. It can be used in field and laboratory. It's a very simple test and shows just at the angle of a drop if a paper or a textile contain PFAS or not. So here, when PFOS, PFOA, and other PFASs are coated on a textile or a carpet substrate exposed to water, and water has a surface tension of 72 micronewton per meter, or oily substances with a surface tension of 20 micronewton per meter and more, they will not spread on the surface. Similarly, also for other surfaces like paper coated with side chain fluoropolymers. So this phenomenon is called water or oil repellence and is used for water, oil, and stain repellents of carpets, textiles, and leather. So most alternatives to PFAS cannot achieve a surface energy lower than 22. So here, this is the surface energy which is needed for repelling oil. So therefore, materials with a high contact angle and low surface energy are therefore likely treated with fluorinated substances. And fluorinated substances and non-fluorinated substances treatment can be described. So if both droplets, water and oil, is repelled, then it is likely PFAS. If only the oil droplet flattens out, the surface is likely treated with non-fluorinated chemicals like some hydrocarbon surfactants or silicone coatings, which also can repel water. Two case studies. So the water oil droplet test was performed in PFAS inventory of Suriname for screening water oil repellency of synthetic carpets in stores. And the finding there was that most synthetic carpets which were tested showed a repellency property of a droplet angle larger than 90 degree. Another study tested the efficiency of PFAS on paper repellency to determine international PFAS use. So this I recommend it to have a look at because they defined at what concentration the PFAS works, and then they concluded if the PFAS concentration which are found in a study is higher, then it's intentional PFAS. If it's lower, then it's unintentional, for example, for recycling. Yeah, so this comes then into play when, for example, now you have a paper where you find PFAS, but at a quite low level. And here they defined at what level PFAS is not working, then it would come from recycling, or if it has higher level, then it would be from a intentionally treatment of that paper. So there is also a standard for compliance for this repellency, and there is a ASTM drop image advantage software to really check this. So this is not, let's say, a simple test, but also has been developed quite scientifically, and there is a software for the assessment. Another screening test which can be used in the field or in the laboratory is sliding spark spectroscopy. So the basic principle of the method is the thermal vaporization of a small amount of the sample surface using a train of defined high current sliding sparks producing a plasma. So this sliding spark spectroscopy is normally used for plastic characterization and sorting, but it can also be used here for other materials like paper. And with the software analysis and the spectra, the content of elementary fluorine on top of the surface is calculated. The system is portable and mobile, but can detect organofluorine only to about a concentration of 0.1%, 1000 milligram per kilogram. And in carpets, the levels can be higher than that. Yeah, so there need to be more assessment, and I also would look forward to a study which publish such a screening. Yeah, to which extent PFAS can be determined with this technology, for example, in carpets, or not at this detection limit. Then XRF spectroscopy in laboratory and in field. So handheld XRF for field could not detect the smaller elements like sodium or fluorine until 2021. So here in 2021, one company optimized an XRF to detect sodium and fluorine. So the combination of direct and how did they do it? Yeah. So one is combination of direct user control of settings, optional helium atmosphere, specific geometry, large area silicon drift detector, 1 micrometer graphene window, and live spectral analysis software. And this together then enabled fluorine analysis with a handheld XRF. So you see, it is quite complicated. And they give two examples. One is the XRF screening of PTFE type. This means a fluoropolymer, and there they could detect it. And a second example they gave was a screening of fluorinated ski waxes, where they also could distinguish between those ski waxes which contain fluorine and those which do not contain fluorine. However, here for this XRF, the detection limit is between 1% and 10%, and therefore this is much too high, for example, for screening of textiles or of carpets. There is a wavelength dispersive XRF, but this is in laboratory. It's a large equipment. So here is able to detect fluorine in the vacuum mode. The concentration here for this WD XRF is 0.05%, and therefore normally this equipment is able to detect PFAS-treated carpets or textiles. Then there is the particle-induced gamma ray emission, the so-called PGE spectroscopy. This was developed as a rapid screening method for total fluorine and applied to quantify PFAS in consumer textiles and papers. It provides also a quantitative measurement of total fluorine on textiles and paper. And here samples are irradiated with gamma ray for around 3 minutes. So the integrated gamma ray counts can be converted to concentration of the total fluorine, and what you get out are nanomole of fluorine per square centimeter. And they have found that the detection limit here for textiles is 24 to 45 nanomole fluorine per square centimeter, and for paper 13 nanomole fluorine per square centimeter, with a reproducibility of 12%. One practical case study which were using PGE spectroscopy. Here they did a screening for paper and for textile for total fluorine with the PGE method, and then they wanted to compare it with the PFAS monitored by GCMS and LCMS, mean the volatile PFAS, the ionic PFAS, and also they did a top assay precursor test. And what you see here, that only up to 2% with the normal mass spectrometry approach, and with the top assay up to 14% from paper and textile have been extracted, and this means 64% and up to 100% of the original fluorine was afterwards still in the paper and in the textile sample. Yeah, this means here I have shown you before this the side chain fluorinated polymers. There is a covalent bond, which normally, of course, those PFAS are not evaporating. Normally, with a normal extraction, they are not extracting. With the top assay applied here, they have been partly extracted, but most part was still here in the materials afterwards. Then a technology frequently used for detection fluorine, which also Natsuko already mentioned, for bromine detection. This is combustion ion chromatography, which is common use techniques for PFAS, some parameter analysis. Products like textiles or paper are pre-baked, inserted into the combustion unit on a ceramic sample and heated gradually to 1100 degrees under oxygen and argon. And then the combustion gases are adsorbed in water, which is then injected into an ion exchange column, and then the fluorine is measured. So the method can aim for both extractable PFAS, yeah, then pre-extraction can be done, and then the combustion, or the total fluorine, mean that the combust of the textile and the carpet is completely combusted. Also, one case study where this technology has been used, an interesting one. So that's a study on PFAS in fast food packaging and disposable tableware in 6 European Union countries. organized by 9 NGOs, and they have worked with 2 pre-screening, one with the oil repellency test with droplet and olive oil, yeah, in the field, and then they have done a quantification of the total fluorine by this combustion ion chromatography, and as the third, they have detected and quantified selected PFAS on these food contact materials. Also, I show you shortly the results because they are interested. So here in the screening, 32 out of 42 fast food packaging tested in laboratory contain PFAS, including KFC, McDonald's, Dunkin' Donut, and Subway. And one interesting result that the McDonald's fries packaging in the Czech Republic contained PFAS, but in Denmark it did not contain PFAS. And the reason is that since June 2020, PFAS is banned in food contact materials in Denmark. So it is possible for fast food also to pack it in non-PFAS containing paper. A second case study, an interesting one, using combustion ion chromatography from Aro et al. 2021. So here they tested individual PFASs at 1100 degree and the outcoming concentration and recovery rate of fluorine. And what was interesting is that for PFOA and long chain fluorinated alkylated acids, the recovery was considerable less than 100%, while for many other PFASs, the recovery was at 100% or close to 100%. So the reason is that here some of the CF bonds survive the combustion even at 1100 degrees Celsius. And this is also interesting from another perspective, because at the moment it is discussed at what temperature PFASs need to be combusted. Yeah. So in the laboratory, you see that not all CF bonds, especially from long chain PFASs, are disconnected at 1100 degree. Another screening method as indicator for fluorine or organofluorine is the F19 nuclear magnetic resonance. Here fluorine has an uneven number of protons and therefore has an unpaired proton which couples electromagnetically when exposed to a magnetic field. So also fluorine is monoisotopic and has a high sensitivity. This together with a high number of fluorine presented in PFOS or PFOA make this NMR quite sensitive screening techniques capable of screening PFAS down to 300 nanogram per gram in samples. Yeah, but yes, this is not mobile, and equipment is also quite costly. So in developing countries, not many NMRs are in developing countries, and one measurement can take 1 day. There are a few more screening techniques described in the guidance. Also some screening techniques which can directly monitor individual PFAS, like the DART TOF-MS, but I do not come into details there. I rather would recommend you to download these guidance and one time have your own look for more details on monitoring POPs in products and recycling, especially in plastics and polymers. Yeah, thank you for your attention. And this is it for presentations from my side. So we check for questions. Okay, I like to know detection limit of chlorinated compounds by XRF. If we apply the approach to beach pellets, is there any effect of chlorine from seawater? Okay, so the XRF for chlorine is less sensitive than for bromine. Yeah, so good XRF, I think, can reach for chlorine about 100 ppm, depending also on the sample. I introduced you the one XRF, which can also screen fluorine. I am pretty sure that this specific XRF can also detect chlorine at lower levels than the 100 ppm. Regarding the question if seawater has an effect, yes, of course, seawater would have an effect. So here, I think this is our own small research study about washing of your pellets and seeing how the chlorine concentration reduce from the seawater, and if by washing with distilled water you can get a chlorine-free pellets. May I know which method is most accurate, and which method do you recommend for beginner to use the tool? I mean, just if we take the question for my presentation on the fluorinated, of course, I mean, this droplet test is quite useful and a good start to screening materials. Yeah, I have shown you detection limits for the different materials, so those you can also look in the guidance, so they are described there. Recommend for beginners, I mean, XRF, you know, this is X-ray. This is for sure not for beginners, and also you need a kind of a course to use this machine, because X-ray is of course hazardous, and even if you use this X-ray equipment to scan something in front of you, there are some backscattering of X-ray. So this is for sure not for beginners and need a good education. And I mean, all the methods which I have described for the laboratory, they are quite sophisticated machines, yeah, which are available only in a few institutions. So here maybe if these questions come from a developing country, I would recommend that you look for some research groups which have such screening methodology and maybe team up. I mean, something similar we have done in our pellet project here, that we sample the pellet in Africa, South America, bring it to laboratories which have XRF equipment and have other sophisticated equipment, and do the monitoring there. But of course, we need also capacity in developing countries. So I know that the next global monitoring plan, which is currently developed, aim that also more capacity is built in developing countries. And there in this project, maybe they can also check what kind of, let's say, screening methodology might be possible. Also, there is at the moment a plastic project in 4 countries in Africa. And more plastic projects will come, especially when we will have the plastic convention or the plastic treaty. And in this frame, for sure, in respect to securing recycling, more monitoring approaches are needed, especially also in developing countries. And I hope that this kind of screening technologies are then also implemented to some extent in developing countries. What is the limit of detection of plasma arc technology? Plasma arc technology. PIGE. You mean probably the PIGE technology, right? So for PIGE technology, we had yeah, it was these are nanomole between 10 and 45 nanomole fluorine per per square centimeter. Okay. Other question, Lisa, are there other questions? Which I have not seen.
So there was just a correction. So for the sliding spark spectroscopy, the previous question was about sliding spark spectroscopy.
And what was the question there?
It was about the LOD of plasma arc. The LOD for the
Sliding spark.
Yeah, that's right.
Yeah, no, I said the LOD is 0.1%. But this is also for, let's say, solid materials. So a colleague of mine in France, which were dealing with carpets, and he tried a screening with the sliding spark spectroscopy. So in carpets and textiles, he could not detect fluorine. Yeah. So but I have also said this. Yeah. So the lowest limit is 0.1% for fluorine there. But only these are then for solid materials. Yeah. Like let's say fluoropolymers. Yeah. When you have the more loose materials like textiles and carpet, probably the limit of detection is higher than 0.1%. Okay. At the moment, there was one more.
Thank you. For now, it seems like we don't have any more questions.
There was one. If we are interested to participate this project, is it possible and how do we start? No, so this project is really only a very short project from some remaining money from the global monitoring plan. So our project we had to develop in a few weeks, and we have to conduct it by the end of June. So for this project, unfortunately, no additional participation is possible. But there will be then a report from the project. So everybody is invited then to have a look to the report, which then also will include more details on the sampling also from other countries, and then also the measurement results. Okay, good. So we are already 10 minutes over time. So from my side, thank you very much for participation, and thanks very much to the presenter for their presentation. So in the chat, yes, we have our next webinars on Monday and on Tuesday. They will be about extraction of POPs from plastic and cleanup of these samples. And on Tuesday then, on the analysis of the different POP groups with instrumental analysis. So then I hand over to Martin, Chair of IPCP, for closing our webinar. Yeah, Martin, over to you.
Thank you very much, Roland. And just very quickly, also from my side, many thanks to all speakers, and to you, Roland, for all the work you have put into this very productive and rich webinar. And I wish you all a good rest of the day and a nice weekend.
Yeah, thanks also to you, Martin. Yeah, bye-bye.